Yeah, Manish, I'm not seeing power from that thing.
This one says it's on, so did you plug it in the right way?
Yep. I just made sure it had power in my room. But now I'm showing nothing. Not getting power.
Power?
Yeah.
You need power?
Well, it would be confidence giving. But it's not showing. Are we sure that we're... My laptop's been having some issues, but this power port was working fine.
Maybe it's the...
There we go. Okay, we're good.
You're connected or it's...
I'm about to do that.
It's working fine.
Yep. And are both of these mics live together?
That was audio now. This is the venue mic. This is for the recording.
Okay. So if I present, am I getting the right presenter view? Wait, there we go. Yeah, we're good here. What's that? No, we don't have. Yeah, it's showing presenter view and everything.
And it shows up in your display settings as two screens.
It's saying, oh. Wait, is this, sorry. How do we want it? Can you come check this one setting here? Cash, can you come check this here? Do you know if we want, I can't remember, do we want extend, duplicate?
You want presenter notes, right?
Yeah.
Yeah, extend is
Extend, right, yeah. Test. But is this your image? That's mine? Why am I not showing?
Maybe restart the presentation.
Okay. There we go. You should stand on the stage. Yeah. We're not using these right now. We need to speak into those, basically.
I should ask Ted if he would.
Yeah, and you could actually maybe get him fit with one right now. But I don't know if you want to do that or it is 9, so we should start in like 1 minute.
We should get our SEs to go and round people up.
I think 1 minute, Cash. right, I think we should get started. Well, he's starting to speak, so it's okay. They'll see you. Hello. Good morning. Cash, how do we get the actual room hot? I just want to get the room AV going. I don't know. Is this for the room? You can tell I haven't done this too much. Okay. No. Okay. Good morning. If you could all please take your seats or stand in the back is fine. We're going to get started. Hello, everyone. My name is Jacob Wobrock. I'm from the University of Washington. Happy Halloween. I dressed up as a conference general chair.
Hi, welcome everyone. It's great to see all of you. I'm Manish Agrawala, also dressed up as a conference general chair.
So together we'd like to welcome you to Bend, Oregon. I'm a native Oregonian myself, so welcome to my home state, although I'm from Portland, which is not exactly where we are, but here's where we are. Hopefully you know where you are, but we are in the central area of Oregon, east of the Cascade Mountains. You can see some of them right outside. In fact, you need to know your three sisters. So we have from right to left here the North Sister, the Middle Sister, and you guessed it, the South Sister. Very creative names, but they used to be called Faith, Hope, and Charity, and then they were renamed to this. Not sure exactly why. Bend, Oregon is the traditional home of the Northern Paiute, the Wasco, and the Warm Springs tribes, today which comprise the Confederated Tribes of Warm Springs. And we encourage you to learn a bit more about the history of the people and this land. For example, you can do so on the homepage of the Confederated Tribes of Warm Springs, warmsprings-nsn.gov/history. You can learn more there. You'll also see out in the hallway a number of photographs from the early turn of the 20th century, this one from 1910. This is Wall Street, and if you go down into downtown Bend, which is about a short walk away, I'll tell you about that in a second, you'll see Wall Street. You'll run into it. This is what it looked like about 120 years ago, 110 years ago. We'd like to encourage you to, especially today while the weather should be quite nice, to walk the Deschutes River Trail. Some of you maybe already have done that. If you stroll very gradually, it's about 40 minutes. If you walk a little quicker, you can do it faster. It's an easy walk to downtown Bend. There are signposts that mark the path. Our lunch breaks this year are from 12:30 to 2:30, so we're giving you 2 hours, so you have plenty of time to get there. And the way you want to start is going uphill from the conference center. There's a few golf holes you'll see. You go past those, and you go up the road, and as the hill goes up and the road turns right, you'll see a trail. But you know, telling you is not as good as showing you. So here is actually the final stretch up to the trail that you'll be able to find. I did this the other day. So you'll ascend the hill. We're on the left side of the street here, just up from the conference center. And as the road starts to bend to the right, you'll see a signpost. I'm going to zoom in here so you see these signposts mark the entire walk to Bend. So just keep looking for these and you're in the right place. It's a really beautiful walk along the river. It's called the Deschutes River Trail, and you'll see the trail start here and drop off down a gradual hill. So go find that. You'll be glad you did, I promise. You are in the right place on this trail if right before you reach Bend, you're going past this lovely power station. So this is, in fact, the trail, and you are not lost. The first time we did it, we thought, boy, this is a little strange, but in fact, the trail goes right past this thing. So if you see it, you're in the right place. Before we go any further, I do want to give a very warm thank you to the entire UIST 2022 conference committee. There were 53 people to plan this conference, and that's not including the 44 student volunteers or anyone on the program committee. So we are talking a major, major community effort. So let's give a round of applause to our committee, please. And as I said, this was a community effort. So speaking of community, I'm going to hand it over to Manish, and he's going to talk a little bit more about our community this year.
All right. Thank you, Jake. So Jake and I really started planning this conference about 2 years ago. And one thing that we talked about from the very beginning is that we missed this sense of community that an in-person conference allows. We really missed seeing all of you and interacting with all of you. It's a big part of what makes up the UIST community. It's you, the people. And so we decided early on that if we could, we would have an in-person conference, if at all possible. Now, you'll notice that there are some hybrid elements. We have a live stream of all of the papers talks, but overall, we really emphasized the in-person experience. And we hope that this is really a chance for all of us to reconnect as a community. So we've registered over 450 attendees to be here in person, 262 students. People are coming here from 25 different countries and 4 different continents. So that's been really exciting for us to see. Now, as a community, we also really care about the experiences of all our members. Discrimination and harassment have no place at UIST. And so I wanted to remind you about SIGCHI Cares. This is a resource for those who might experience discrimination or harassment at this conference. The chairs of SIGCHI Cares are Celine Latulippe and Michael Muller. And you can learn more about SIGCHI Cares at the sigchi.org website, or you can contact them at the email that's listed here. And in particular, I wanted to point out that Celine has also given us her email. She wanted us to tell you all of you her email, because if you experience any problems, you should feel free to reach out to her and talk with her. All right, so you might have noticed that we have a new badge design this year. We eliminated drink tickets, and instead there are slots on the back of your badge, and these slots are for Sunday, Monday, and Tuesday nights. Every time you get a drink at the evening events, you should mark off one of the slots, and that way we can keep track. And we want to remind you to drink responsibly. Our banquet is going to take place on Tuesday evening, and it's going to be in Sun River, which is about 20 minutes away, 20 minutes south of here. And we've arranged buses to leave every 30 minutes for Sun River after the last session on Tuesday, which ends at 4 p.m. So make sure you get on one of those buses. Return buses are similarly scheduled. And on these bus rides, please make sure to wear your masks. And we will also be announcing the Lasting Impact Award at the banquet. In addition, at the banquet, we will be remembering Edward Blank. Edward was a longtime member of the UIST community who tragically passed away earlier this year. All right, so given the emphasis on the in-person event and the pragmatics of COVID, we wanted to remind you of the conference policies for this year. So our goal is to help everyone at the conference feel comfortable in participating in the event. And so as per our policies, all attendees must be vaccinated or have a religious or medical exemption. When indoors, masking is required unless you are eating, drinking, or speaking, in particular presenting. And finally, we ask that you do a daily self-test in your room each morning. Here on this slide, you can see my self-test from this morning, thankfully negative. Jake permitted me to come to the conference. You don't have to check your test with Jake, but we encourage you all to do, the policy is to do a self-test every morning. Now, if you don't have a test with you, please talk to the folks at registration, as they may be able to help you procure some tests. All right, and finally, I just wanted to say thank you to everyone here for helping us to keep each other healthy and safe. All right, back to Jake.
We have some very exciting keynotes this year. Of course, our opening keynote is coming up soon, and I'm sure you'd rather us be done with this, these remarks so we can get on to that, and we will shortly, we will. Opening keynote is from Ted Chiang. He is a award-winning science fiction writer. You may have seen the film Arrival. That film was based on a short story of Ted's. Note that that is one of the few things in this conference this year that will not be live streamed, but most of the other content will. Our closing keynote is an interview with Marissa Mayer. I will actually be interviewing Marissa, and Marissa was the first woman engineer hired at Google way back when it started. Then she ascended to the level of a vice president there, had a lot of influence on many products, then eventually became the CEO of Yahoo, and now is a CEO of her own startup that I'm sure you'll hear some about. Because I'm interviewing Marissa, she said it would be wonderful if you would send me any questions that you might have for her between now and say Wednesday morning. Sooner the better. I will take your questions and I will curate them and ask her some of the best questions that you send me. So you can send those to me at my email address, wobrock@uw.edu. If you don't remember how to spell my name, it's on the committee page, so you can find me there. You can also just send it to chair2022 at UIST.org. That's the main chair email. In that case, Manish will see your question also. We have a social program, thanks to the social chairs who put this together. I'll briefly review some of the highlights that they've assembled. So there'll be lightning talks. These are 1-minute videos in which presenters can present themselves. There'll be 23 presenters. These videos will be played at the beginning of paper sessions. They'll also be accessible online. And don't hesitate to reach out to the presenters if you're interested in what they have to say. There'll also be 2 Ask Me Anything sessions. These are discussions with academics on producing research, career development, funding, diversity, accessibility, and related topics. So we'll have one from Lining Yao. That's on Tuesday, tomorrow, 1:30 to 2:30. So that's the second lunch hour. That'll be over in Cascade AJ, which is the other, well, actually, it's the room that will happen when the wall goes up over there. And then Pedro Lopez will be talking on Wednesday at that same time slot, also in AJ, which is that third of the current room. There's also a Halloween event, today being Halloween. And so you'll actually have the option to dress up tonight at the demo session. So that's this evening. It's actually downstairs. So right outside you'll see stairs leading down. We have the entire bottom floor of this convention center for the demos. And at the demos there'll be face paints, candy, costumes, and there'll actually be an award for the best costume at UIST. So go dress up and enjoy some Halloween festivities. Of course, UIST doesn't happen without the support of sponsors. In particular, thanks to Chris Harrison and Steve Oney for their role as sponsorship chairs. We are an ACM conference, and we are sponsored by SIGCHI and SIGGRAPH. Our platinum sponsor is Meta Reality Labs Research. Our silver sponsors are Adobe and Autodesk. And our bronze sponsors are Google, Intel, UCL, Tableau, Intuitive, and Toyota Research Institute. In particular, Google was our wellness sponsor donating so that we could provide extra masks and a limited number of COVID self-tests. So thank you to all our sponsors. Let's give them a round of applause. And now we'll hand it over to our program chairs who, of course, oversee the technical program this year at UIST.
Awesome, thank you. I'm Eitan Adar. Hi, it's great to see everyone, or mostly your eyes, but it's very nice. Vidya is the co-chair, and I'll hand this over to her in a second. So we have a few things we'd like to briefly mention. These are the two of us. Please find us and come talk to us. We hope you enjoy all the technical program. We had 3 great student volunteers who put up with a lot of meetings and hanging out during the program committee meeting. This year, we had 372 submissions. 98 were accepted, 7 with shepherding, so a little bit less than last year. 2 papers are from Tokai. The acceptance rate is roughly what we had in previous years, so 26.3% relative to 25.9%. To make all this happen, we had 69 really amazing program committee members. 12 of them had never done it before, so thanks to them. In addition, many of you are part of the second group, 475 reviewers producing almost 1,500 reviews in total. So it was quite an event. Many of you were doing these things while sick from Chi-induced COVID, so we appreciate the extra work and getting it done. So thank you for that. I also just want to highlight very briefly special reviewer thanks. 130 reviews were tagged as being super awesome by reviewers or authors or whatnot, and 133 reviews and 109 reviewers. And I wanted to highlight a few reviewers who went above and beyond and had multiple tagged reviews as being great. So can we just get a round of applause for all the program committee members, reviewers? Thank you. So usually Bjorn would be doing this as the chair of the Best Paper Committee, but I guess I get the honor today. The committee members included Emily, Jeff, Mike, Rio, and Tice. These papers will be throughout the session. We had 3 Best Paper Awards and 3 Best Paper nominees. So Best Paper Awards, we have prototyping soft devices with interactive bioplastics. Please hold your applause for just 1 second. One sec. Grid coding, an accessible, efficient, and structured coding paradigm for blind and low vision programmers, and cross-ally, identifying video accessibility issues via cross-modal grounding. We will be presenting their awards to them during the sessions, and we'll call up the individual authors and thank them again. But please feel free to clap while everyone's in the room. And then for honorable mentions, we have notational programming for notebook environments, a case study with quantum circuits, augmented chironomia for presenting data to remote audiences, and prolonging VR haptic experiences by harvesting kinetic energy from the user. So please clap again. Oops, I'm sorry, one more. Please clap again. There were 4. Semantic on, specifying content-based semantic conditions for web automation programs. Sorry about that. All right, I will hand it over to Vidya for a few more things.
Great, good morning. I'm Vidya Settler from Tableau. And in addition to all the other stuff that was mentioned, there's really more coming as part of this program. We have a student innovation contest, so there are going to be tickets available, denoted by the 3 red tickets, so please vote. We're going to have a Best Paper Award denoted with the blue tickets, and 5 of them are going to be available. Best Demo indicated with the yellow tickets, and Best Talk. But there's still more. So this year, just like previous years, we will be having UIST Visions, which is a venue for forward-thinking ideas to help inspire the community. And this year, Jim Holland is the Visions Chair, and we have 2 great speakers, Barbara Traversky and Jamie Timon, who will be giving these UIST Vision talks. I also want to take a moment to acknowledge the various chairs of posters, demos, doctoral symposium, and student innovation contest. So just hold your applause till the end, but I'm just going to read out their names to acknowledge their contribution. So poster chairs Doa Doan and Jiun Kim, demo chairs Jun Nishida, Michael Wesley, and Ray Zhang, doctoral symposium chairs Alexander Ion, Dan Olson, Xiumin Zhai, and student innovation contest chairs Thijs Rumen and Ryo Suzuki. Let's give a round of applause to their contributions. And just some information here. So you can access the program online, and here's the link. There's a QR code here. The ACMDL has links to the papers as well as the proceedings. And Discord is going to be used this year as well for a lot of the asynchronous communication, hikes, Halloween costume coordination, all the important stuff. So please join Discord and be part of that conversation as well. And Wi-Fi is important, so here's the information. And I will hand it off to the general chairs to introduce the opening keynotes. Oh, the tickets? Okay, actually the tickets for the voting are found inside your badge. So just wanted to make note of that. Yeah, and I have them too. Okay, so I'm going to hand it off to the general chairs, and they're going to introduce the opening keynote.
All right, so, I am absolutely delighted that we have Ted Chiang here today with us. As you know, Ted's short stories have won many major awards, including 4 Hugos, 4 Nebulas, and 6 Locus Awards. His first collection of stories, The Stories of Your Life and Others, has been translated into 21 languages. And of course, as Jake mentioned, the title story from that book was the basis for the Oscar-nominated film Arrival. His second collection, Exhalation, was chosen by the New York Times as one of the 10 best books of 2019. And I wanted to mention in particular for this audience that Ted holds a degree in computer science from Brown University and is a graduate of the Clarion Writers Workshop. Now, for me, Ted is one of those writers whose stories are just brimming with ideas. And they're ideas that you continue to think about long after you've finished reading the stories. I had the opportunity to go to lunch with Ted yesterday, and we discussed all kinds of ideas, from the nature of consciousness, to free will, to religion, Ted is going to be here for the next few days, and I encourage you to talk with him and show him the things that you're working on. So I am very, very excited for this talk, and please join me in welcoming Ted Chiang to UIST.
Okay, we are just going to wait for another 1 or 2 minutes for folks to trickle in from the coffee break, and then we'll start. So,
One is for 20, one is for
okay, so this says for.
the audio does not come out of the speakers to put on videos.
Oh, I already checked everything. Yeah, at least in the first one. Well. All right, everyone, I guess we can get started. Well, welcome everyone to the extended reality interaction session at UIST. This is the first session, and great to see everyone in person. So I'm Karan Ahuja. I'll be chairing the session today, and I'm from Carnegie Mellon University. You all are in for a treat. We have 6 amazing papers in this session that the presenters will go over, and we'll first start with the lightning talks for this session. So in the lightning talks, we have first-time WIST presenters and students. So here we have Logan, who will sort of like give his lightning talk, and talk to Logan afterwards if you're interested. He's looking for PhD positions. And then we have Meng-Gyun Kim, who is looking for collaborators. So without further ado, let me play the talks.
Hi, my name is Logan. I'm currently a senior undergraduate researcher from UC Chicago, working with Professor Ken Nakagaki. So my research interest is in the intersection between interaction design and learning, perception, and collaboration. My research vision is to use novel interfaces to facilitate learning and collaboration experience. Besides research, I also have a deep passion in building startups. So during the pandemic period, I started a social media company back in China. In this year's series, I'm happy to present Sketch Reality, which is a bidirectional sketching interface between tabletop robots and AR technology with my collaborators from University of Calgary. Some potential applications include physics education and tangible gaming. And I also invite you to come to the Student Innovation Challenge and see our project, Shadow Astro. For the next step, I'm thinking about applying PhD positions starting in 2023 fall, and also I'm opening to collaboration opportunities with other HCI researchers. I'm happy to meet you all, and feel free to contact me.
Hi, I'm Myung-Jin Kim. I also go by MJ. I'm a second-year PhD candidate advised by Andrea Bianchi in the Make Interact Lab, a small research team in the Industrial Design Department at KAIST in the Republic of Korea. My research interest is in interaction design, specifically for virtual environments involving touch and haptics, enabling novel multimodal sensory experiences in VR. The past research I was involved in mainly focused on developing actuated handheld VR haptic controllers, rendering sensations such as weight motion, object flexibility, and object surface motion. Aside from this focus, I also printed conductive ink on my body, explored pseudo-hand-eye interactions on the HMD, and developed a wearable input technique for 3D object manipulation. This year, I'm participating as a student volunteer, and I'm also presenting a demo and a poster. I'd love to make new friends, share thoughts and ideas, and also collaborate together in future research projects. Please feel free to stop by and chat or drop me a message through Discord or email. Thanks for listening.
All right, so those were the lightning talks. Now we'll start with the presentations of the papers in this session. So the flow of it will, the presenters will come and present their work, after which we will take questions from the audience. If people are on Discord, you can post the questions on Discord, and we will go over those as well. So our first presenter is Hiroki Kaimoto, who's going to be presenting his group's work on sketched reality. Now Hiroki is also looking for faculty and postdoc positions after this, so if you get a chance, please do network with him and reach out to him. Hiroki, I'll leave you to it.
Okay, thank you for the introduction, and also thank you for coming to our presentation. I'm very excited to have a presentation as the first presenter of this year's WIST, so let's get started. My name is Hiroki Kaimoto. I'm a PhD candidate at the University of Tokyo. In this talk, we want to talk about sketched reality, sketching bidirectional interactions between virtual and physical worlds with AR and actuated tangible UI. This work is done by the collaboration with my co-authors, as showing on the slide, include Mehrad Fardan next to me. So this work was my intensive project at University of Calgary. So with the advanced augmented and mixed reality technology, many HCI researchers recently explored AR sketching as a means of interactive creating and prototyping AR objects. In the existing AR sketching tools or in the existing AR interfaces in general, sketching allows users to flexibly customize and develop user interface. But they are commonly one-directional. It means that virtual sketches do not affect the physical environment interactively. On the other hand, some HA researchers also explore that virtual objects or characters affected the physical environment through projection and actuate this physical object. So in this paper, we present an approach that combines AR sketching and actuated tangible user interfaces for bidirectional sketching interaction. This bidirectional interaction refers to the interaction in between virtual and actuated physical objects that affect each other through physical actuation and digital computation. So from the user experience perspective, the sketch graphical AR contents can move the physical object, and physical objects can affect graphical object, vice versa. To demonstrate this concept, we developed a proof of concept prototype that employ tabletop mobile robots and an iPad-based AR sketching interface to seamlessly couple physical robots and virtual interactive sketches. As you can see in the video, sketched graphical components can be used to affect the robot motion, and inputs the robots can affect the graphical system. Together with implemented demonstration, we present a set of design space of the bidirectional sketching interaction in the 4 categories. This should become a basis for future researchers and designers to explore sketch-based bidirectional interaction.
So our work is informed by a variety of prior research. There are a couple of research projects using augmented reality to control robots and actuated tangible user interfaces. In these examples, augmented reality virtual objects affect physical objects as interfaces or data visualizing displays for controlling actuated TUIs using a single robot or a swarm of robots. In the research area of augmented reality sketching tools, the researchers explore the coupling of virtual and physical worlds through AR sketching tools. In this case, the virtual sketched objects are generally static. But in recent years, as shown in Reality Sketch's example on the right, researchers have also explored AR sketching to dynamically couple virtual objects and physical objects. In this sketching method, the physical objects affect the virtual objects as a visualizing media to show data and applications. So, as shown in these related works, existing AR tools combine virtual and physical worlds to develop interactions that affect from one side to the other, but not in a bidirectional way. Therefore, we decided to focus and build up our concept of bidirectional interactions between the physical world and the virtual world through augmented reality sketching tools. So let's move on to the section of our proposed concept, sketch reality.
Thank you. So sketch reality is a novel interaction approach based on AR sketching for controlling actuated TUIs to realize bidirectional interaction between physical and virtual worlds. In our system, the user can interact. In our system, the user can interact with small robots through sketch virtual object via iPad-based sketching. This allows the user to control the robots in a variety of ways, such as manipulating via sketch virtual object, dragging robots on the iPad, or even directly graphical the robot with hands. The motion. The physical and virtual object would move according to virtual properties defined by the users, so that, for example, object can be affected by virtual gravity. As shown in the table in our design space, we define 4 types of bidirectional sketching interactions to explore how virtual and physical objects affect to each other. For the boundary constraints, the physical object would be a constraint of the virtual object like walls to bounce on and vice versa. For geometric constraints, the object would keep the relationship of their position based on sketched constraints, like the distance and angle between each other, even if one object moves. For the applied force, the physical object could be affected through force action and the virtual environments such as gravity. In a dynamic collision, the physical and virtual object can hit and collide to each other dynamically. So let's talk about how to build up our system. As an overview of our proof of concept interactive system of sketch reality, we employed an iPad-based AR sketching method interface and the small table robots for actuated TUIs. Also, the self-robotic toy Toyo, developed by Sony, was employed for actuated TUIs. Now, I would like to introduce the workflow of the interaction with our prototype system following the 4 steps. First, First, the user have to do simple calibration to match the interaction maps to AR sketching area. User can do this by tapping 2 points on the iPad with the stylus. As you can see, the center point and the top left corner point of the mat. After the action, the user can sketch virtual objects through AR sketching. In the demonstration as showing on the slide, the user sketches the circle as a virtual ball, the lines as a virtual thread, and the square as a virtual foothold. The user also set up the virtual environment by tapping to interact with physical object and select each object's status, static or add gravity. After this setting up, the virtual and physical object can interact with each other. We realized this bidirectional sketching interaction system through JavaScript-based physics simulation and WebXR for AR sketching, and Toyo.js for interactive data communication of Toyo's motion and Toyo's position. The detailed implementation can be found in our paper. So let's move on the applications. For the application scenario of our system, we present 4 types of scenarios: physics education, explorable mechanism, tangible gaming, and INS programming. In the scenario of physics education, for example, we implemented the simulation of Newton's cradle. Using this, physics learning students can simulate and interact with common physics phenomena by reconfiguring parameters. In classroom scenarios, for example, seeing the object in motion with virtual pendulum attacking effects with invisible physical would simulate the imagination and provoke questioning and thinking about the real phenomena. As for the application of explorable mechanism, users can simulate a variety of mechanical motions through actuated TUIs and virtual sketches. The user can touch and feel mechanical system simulation on the minimum configuration that be performed within a single configuration without having to prepare components for each simulation. In the application of tangible gaming, for example, we implemented the hockey game. In this scenario, 2 users can play a hockey game with a small robot as a handheld discs and a virtual ball and ball. In the demonstration, the users can strike the ball to each other. As for INS programming, for example, we implemented the virtual rope motion control. The user can move multiple robots using a virtual rope as if to pull them closer. In such way, while manipulating a swarm of robots can be generally difficult, Sketch Reality allows users to flexibly customize a way to control robots' behavior in Stu. So now we are talking about the detail of our presented concept, sketched reality, that realizes bidirectional sketching interaction via sketching virtual objects that can affect physical objects or be influenced from physical objects. At the last, we would like to talk about discussion and future work. The approach explored in sketched reality has great potential for future research opportunity. For example, while we have employed table-based AR modality, other types of hardware modality of augmented reality could be utilized. For example, projection mapping or see-through head-mount display. In addition, by setting up haptic feedback through real small robots, the user gets a more practical experience. We believe our proposed concept would expand the research area in the virtual and physical world interaction and be applied in various research fields such as telecommunication, XR education, and computer-aided design. We hope that our proposed concept will inspire other researchers. Thank you for your attention, and we are happy to take any questions.
All right, thank you for the presentation. Great application space exploration, for sure. Do we have any questions? Yep.
Hi, thanks for the talk. My name is Shakir. I'm from Meta Reality Labs. I had a question. It looks like there's at least some level of latency between the physical and the virtual. Whether the virtual might move first or the physical robots might move first. Have you done any user studies or just any way of thinking about the impact of that latency and how much it matters, when it matters, that kind of thing?
So part of our future work is to actually conduct a user study as well. But in terms of latency, we didn't notice many problems. Yeah, it was generally okay. Latency wasn't a problem that we encountered very much.
Hello, thanks for the great presentation. Frank Liu from Arizona State. I was wondering, I noticed there's like a 4 times X speed for the videos. Kind of what's like the max speed? Because like if I was a student and I was trying to draw things fast, taking that long would be a little bit frustrating. So I was wondering if you could elaborate a little bit about that speed.
Oh, speed of the video. Yeah, it depends on the application.
Yeah. I don't know how to answer that. So I think we increased the speed of the video so that it's more clear to you guys what we were doing. A lot of the videos were filmed sort of last minute, to be honest. But yeah, that's one of the things that we'd like to do. Like, since we haven't done the user study yet and it's part of the future work, it would be interesting to see what the pain points are from the user's experience and the user's perspective of using our system. That's definitely a good question and something we should look into.
All right, let's thank our presenters with that, with a round of applause. Great. If you have more questions, please feel free to find them during the lunch break. Now we have Graham Wilson from University of Glasgow presenting his group's work on Passenger XR, a low-cost platform for any car multi-user motion-based passenger XR experiences.
Okay, yeah, hi, I'm Graham from the University of Glasgow, and I'm here to talk about Passenger. It's an open source hardware and software motion platform. for creating XR experiences in cars. I couldn't bring a Halloween costume, so instead I've added some decorations to my slides instead. Before I start, I want to say that the first author and brains behind this project is Mark McGill. He couldn't travel, unfortunately, to be here, and so I'm going to present on our behalf. So, XR is increasingly being used in vehicles. Originally started off with kind of AR applications for driver interfaces, but increasingly it's also moving towards passenger experiences. And as autonomous cars become more common, and so as drivers transition to passengers, people have more time to make use of XR for leisure and productivity while in cars, buses, trains, planes, all sorts of things. And so it means that there's an impetus to create experiences which can either make use of or counteract the motion of a vehicle in the creation of XR experiences. So you might want to counteract the movement of the car to have a kind of stable, configurable XR workspace around you while you're in the car. Or you may want to make use of the movement of the car to create engaging, motion-based XR entertainment. But there's a number of challenges in creating XR experiences in cars. A large one is the headset orientation itself, so both differentiating the headset orientation from the car orientation, but also maintaining alignment of the headset with the car. So because headsets use IMUs to detect the orientation of the headset, that means that any rotation that it detects, it thinks that the headset is moving itself. So what that means as the car rotates, the headset thinks that you're rotating, and so the content you're looking at will shift around you as the car rotates. And that's annoying if you're having content you want to focus on and it's constantly shifting around you. It means you can't keep track of what you're doing. So it can be important to maintain the content ahead of you or potentially convey some aspect of that motion to reduce motion sickness due to the mismatch of viewed motion and felt motion. But similarly, IMUs inherently drift. So what starts off as a forward bearing, as the car drives around, the IMU inherently drifts, and so what it thinks is forward can slowly start to drift, and so you're no longer facing the same forward as the car. So it's important to maintain alignment between the two to make sure that everything's stable. It can also be prohibitively costly to do this kind of research. You need a car to start off with, and you need to maintain a car. A lot of approaches tend to use a laptop compared to a PC, connected to a PC VR headset, which is quite expensive and doesn't scale to multiple users. You might need a router for Wi-Fi connectivity and so on. And it can also be useful to have access to real driving data in the lab. So if it's costly to make use of a real car for testing, you can make use of real data to analyze or feed into experiences in the lab to make it easier to develop experiences or fine-tune them away from the car. And finally, it's generally been a challenge to have multiple users make use of experiences, either by using just one PC and one headset, or maintaining the shared data of the car with multiple users in the vehicle. And so that motivated us to create Passenger. It's not passenger, it works more as a visual kind of pun than a vocal one. And it's an open source hardware and software motion platform for which works in any car in the last 15 years. It uses low cost, off the shelf Arduino components, and it works on standalone VR headsets and connects to multiple users in the vehicle. So it consists of a set of vehicle components. This is a load of Arduino boards, sensors, and processors. In the middle is an ESP32 Thing Plus processor as the main brains, connecting to an IMU for the orientation of the vehicle, to an OBD, so an onboard diagnostics port for the velocity of the vehicle, although different cars provide additional information through the OBD2 port too. And then a GNSS antenna for the position, the location of the car in the vehicle. And so the Thing Plus packages all that data up and sends it wirelessly using Google Protobuf to the user, which consists of a receiver, Thing Plus, it's the same processor on the headset, which then passes that on to the Unity motion platform software running on the headset. And we chose a Pico Neo 3 Pro for reasons that you can find out in the paper. And so I'll talk about 4 key features of the passenger software. starting off with the kind of the flexible and configurable motion platform itself. So this is all in Unity. So all vehicle sensor data, so the physical sensor data coming through, as well as the user sensor data, so that's the headset and the controllers, feeds into a number of scriptable sensor objects. So they all feed into a range of different dedicated scriptable objects, which store that information and provide it at real time, at runtime. And what we have is a motion platform configuration. You can kind of see down the right-hand side there, which basically lets you drag and drop these sensor scriptable objects into slots to dictate what sensors enact what motion within the virtual scene. And so that's typically moving a reference frame, which is what we call with the virtual vehicle in the scene. So you can drag and drop and indicate what you want to control: the rotation of the reference frame, so the rotation of the virtual vehicle, the velocity of it, the movement of it through the virtual scene. And although you might typically use it for the reference frame, you can technically attach these motions to any object in the scene, so to have any kind of movement there controlled by the sensor data coming through from the vehicle. And all these individual sensor data providers are extensible. You can easily add additional functionality or additional new sensors into them. We've recently added fingertip temperature and heart rate sensor to the vehicle protobuf. And they're also chainable, so you can plug them into your own kind of custom, say, alignment correction, so you can feed in the IMU into your own correction alignment, or altering the perception of motion. So you can feed in the real velocity, multiply it, or change it in the way so that the person has a different sensation of motion compared to what's actually happening. As I mentioned, it's important to be able to maintain the alignment of the headset with the car and to compensate for any change in drift. So passenger includes a few different ways of doing this. One is through detecting shared accelerations between the headset and the car. So as the passenger is moving around, driving around, regardless of where they're facing, passenger can detect the shared acceleration. Let's say the car moves off from a stop or comes out of a corner and moves off. It can detect the shared magnitude of accelerations and identify the car forward and the headset forward, and use that to then realign the person's forward bearing with the forward bearing of the car. It also supports external anchors, so the use of pass-through cameras or a connected camera. It can detect QR codes to maintain the forward bearing, or even potentially a form of 6-off tracking by detecting the location of the QR code in the field of view. And just simply manual realignment, so the user can look forward, press a button, and manually realign the forward motion. It also supports multi-user network in the vehicle. So as I mentioned before, a lot of approaches tend to use one PC for one user. But instead, the ESP32 chip that we use has a Wi-Fi broadcast in it, so it can wirelessly broadcast the vehicle telemetry to up to 10 passenger devices in the vehicle. So that can be a handful in a car, it could be many more in a bus or in a plane. And it means that each user has an individual copy of the live vehicle telemetry that's coming through. So that can be for matched experiences, so everyone gets the same real-time experience from the car, but it can also be for personalized experiences. So either two people doing entirely different experiences, one playing a game, one working in a workspace, but also it can have personalized conveyances of motion. So different people are differently susceptible to motion sickness, and so the different cues that they might want to get to convey the motion of the car can be personalized per headset. And then using the Mirror API, it even supports shared experiences. So you can look around and see the other person's avatar in the vehicle that you're sharing. And lastly, it supports recording and playback of all sensor data for playing back later for desk-based development. So doing in-car testing, as I say, it's costly and time-consuming to have to go into the car, drive around, see how that motion results in changes in the experience. And so instead, Passenger lets you test interfaces, different alignment, realignment methods, the occurrence of different game events in the lab instead. So using a recording manager or a playback manager object, all the sensor data can be recorded into serialized JSON files for later analysis. So you can just look through the data, look back through the logs. And primarily, you can use that to read back in. And so using the same motion platform configuration as you would when you're driving around live, you can just feed the data from the files into the sensors, the scriptable object sensors, and they will enact the exact same motion in the scene, as they would have done if it was live, but you can do this at the lab to prototype different aspects of the experience. All the code will be available open source on the project website after the conference. There's a free non-commercial use for bioresearchers, and there'll be a licensing option for industrial partners. And to finish off, I'll show you 3 quick demonstrator videos just to show a few examples of the kind of things you can make with using Passenger Motion Platform. Okay, thanks very much.
Thank you so much. Okay, now we will take questions from the room. Okay, I see your question there.
Hi, Graham.
Hiya.
Thank you for the great presentation.
Thank you.
I'm Sue from UCLA.
Oh, yeah.
I like this work a lot. So I think most of us have the experience that we want to work in a car, but the screen of the MacBook just keeps shaking. I think if you're working in the VR and you have the stabilizing system, it would be very simple to do that. And my question is, yes. So one challenge you want to address here is motion sickness, and but at the same time, I'm also wondering, like how effective it will be. So do you have any data and user study to share, or I would like to know more.
Yeah, you're right. Motion sickness is a huge problem. I mean, people get cyber sick in VR when they're standing up, and people get motion sick in cars when they're not doing anything. So you combine those two together, and it's a recipe for disaster. So a large part of the project is looking at both detecting and mitigating motion sickness in VR, and we're looking at a range of visual options. So because you can detect the motion of the car with the sensors, you can convey different aspects of that in a different way. So you can convey the velocity through, say, peripheral motion. You can use, we're looking at multimodal feedback as well. And because people are differently susceptible to that, people need different types of effectively visual motion conveyance to be able to get the kind of information they're needing. So we are in the process of publishing a paper on visual mitigations, and I think it's it's a part of the problem that we're working on just now. Yeah.
Thank you.
So one thing I was wondering is in these multi-user scenarios, what happens when
We haven't experienced it so far. One of the reasons we use the Pico Neo 3 is that it doesn't drift very much at all compared to, say, the Quest 2 drifts quite a lot. So the levels of drift are never huge, particularly because you can detect the differences within a few degrees. And so it's very rare that you'll have somebody facing this way and somebody facing that way. They're quite subtle. And as soon as you do detect a few degrees of difference, you can use the methods in here to then realign. And so the person...
So it's like pretty quick to adapt to any of those drifts.
Yeah, absolutely, yes. I mean, generally, it drifts within about 4 degrees within about 7 minutes. It takes quite a while for that drift to occur. And once it does, you can kind of imperceptibly move it back without the person noticing.
Yeah. Well, thank you so much. With that, let's welcome our next presenter, Lipin. He will be presenting DEEP, a 3D gaze pointing technique in virtual reality, leveraging eyelid movement. Also, while Liping is setting up, another thing is Liping is wrapping up his undergrad and actually looking for SCI labs, accepting PhD students starting this fall. So, if you have any open positions, please do reach out to me.
Which mic should I use?
The black one.
The black one?
The other one is for you.
Oh, okay.
So, yeah, the black one is for you.
Awesome. Okay, good morning, everyone. I'm Leping from Tsinghua University, and I'm honored to present our work on 3D gaze pointing and leveraging eyelid movement. So eyes are the windows to our souls, and gaze pointing is really helpful, especially when the user's hands are occupied by tools. For example, on the right, a surgeon might be using AR as reference when conducting a spinal operation, and they can be benefited from using gaze pointing. However, gaze pointing still suffers from the unintentional triggering due to continuous eye movement. And in this case, the surgeon might accidentally click on some UI elements that were not intended. It also suffers from low input precision due to the natural eye jitter. And it's difficult to select occluded 3D targets, for example, like the anatomy model on the right. So if you unfortunately wear glasses like me, then you probably have the experience when you take your glasses off, you want to squint your eyes to focus when you cannot really see very clearly. And so DEEP was inspired by this observation, and it is a high precision and occlusion robust gaze pointing technique. So basically, it takes the widening and squinting of your eyelid. Sorry for the big eye. We call it the AAE, or the aperture angle of eyelids, and as an additional input. And then the user can adjust the visual depth, which is showing on the right, to see these occluded objects, and subsequently select them. So for example, when the target is occluded, as marked with this blue arrow, the user can increase their AAE to see the occluded object, and then point and select with gaze dwelling. Of course, the user can also decrease their AAE and hide the occluded object, then select the objects that are closer to them. In addition, the user can use to select partially occluded objects by just gaze dwell on the area that can be seen without adjusting the visual depth. So DEEP features 2 design components. First, the AE input, which adjusts the visual depth and enables occluded target selection. The AE is described on the scale, where -1 is fully closed, 0 is neutral, and +1 is extremely widened. There's a calibration process to normalize users' AE. And second, there's a probabilistic gaze point decoder, which disambiguates the gaze pointing and then enables accurate selections. So to realize these features, we conducted 3 user studies. The first 2 are focused on examining the user's eyelid movement, and the third one is focused on their gaze dwelling behavior. Also, we have an evaluation study. So I'm going to quickly walk through these studies and show you some results. In the first study, we wanted to answer whether or not the intentional eyelid movement is distinguishable from the natural eyelid movement, and also how comfortable it is for users to perform such movements. So we asked the participants to gaze and dwell normally for 2 seconds on all of these targets. And the results show that the AAE increased as the user gazed upwards, and the range was actually small, which suggests that natural eye gaze movements leaves the room for intentional eyelid movement as an input. Next, we asked the participants to rate how easy they feel when they are widening and narrowing when gazing at these targets. And we drew a 90% confidence ellipse of the gaze distribution from previous task, which is shown in orange, and the results show that the participants felt comfortable for all targets within that range. So next, we want to answer the question of to what extent can the users actually control their AAE? So we imagined that there could be 2 types of control, and we designed 2 types of targets respectively. So either one that's a 1-1 mapping of the control, where the user's AAE is directly used as an input, as represented by the line targets. Or there could be a proxy system where the visual depth is just the one once the AAE is within the yellow region, as represented by the segment targets. So our results show that the adjusting of AAE to line targets is more difficult than that to segment targets, because that user can easily overshoot a target. We also found that the user's AAE holding ability for segment targets, which is the easier one, is sufficient for interactions. So next we move to the third study, where we wanted to answer what is the user's gaze dwelling position. So we asked the participants to dwell on these targets with different radii for 2 seconds each. And the results show that the user dwell is not precise enough for very small targets, and also show a consistent precision, which is good, and the user's gaze points are slightly offsetted towards the top. So from all of these studies and the findings, we implemented DEEP. The first part is the visual depth adjustment, and the second part is the dwell and target disambiguation. So here in this video, for the visual depth adjustment, we adopted the proxy control, which is the segment target. The visual depth is adjusted once the user's AAE is within the region that's marked in green. And for the dwell-based target selection, the first the gaze is hit. The gaze hit test region for each of the targets is enlarged so that we can compensate for the low precision. The dwell is detected once 90% of the gaze points fall within the hit test region of the targets, and corresponding targets are identified as candidate targets. There's a video showing here. As you can see, 2 targets are identified as candidate targets. So next we have to disambiguate which one is the target that user is intended to select. So we designed an algorithm that disambiguate them and divide them into both the depth dimension and also in the planar XY plane. So in the depth dimension, the objects in the front has a higher probability of selection because the visual depth adjustment has already rendered objects, including the target, unselectable. Just an intuitive representation of that. And then on the XY plane, the offset distance between the center of gaze points and the center of candidate targets is used to calculate the probability of location selection. And then we can disambiguate and figure out which target is the intended target by the user. So finally, we did a evaluation study on our DEEP system. So we evaluated Deep's interaction performance with 4 techniques in 5 conditions, each with 20 selections in randomized order on 13 participants. The evaluation is based on selection time, failure rate of each technique, which is a combination of error rate or abort rate, where the user find it impossible to select. And also, we ask the user to give their subjective feedback. So the 4 techniques that we're using are first a baseline technique, which is a naive dwell with no visual depth adjustment or a probabilistic dwelling selection. The second one is called LDeep, where L stands for the location. So it statically emphasizes the location selection without visual depth adjustment. The third is DDeep, where D is standing for depth. It statically emphasizes the depth selection, which is the one with visual depth adjustment. And finally, we have HDeep, which is the one that we have been discussing, the complete set of deep. So we designed 5 scenarios to mimic different types of real-life pointing scenarios, which are grouped into different occlusion levels and also different types of complexity. So our results show that HDeep, which is the complete set, is the fastest on average. And in total, DDeep, which is the one with the depth adjustment, only achieved the lowest failure rate. And the users using the HDeep adjust visual depth less frequently on the less occluded scenes, which means that they're using the location selection, where they're just gazing at the targets that are partially occluded. And finally, we have gathered users' feedback. So their 5-point survey feedback showed that LDeep and HDeep are better received than the naive dwell and DDeep. Specifically, LDeep is best in learnability, ease of use, and it is the least fatiguing, whereas HDeep is the best perceived in performance, least frustration, and highest overall satisfaction. So coming back to the motivation of our project, Deep solves the challenges that are posed, namely that the intentional eyelid movement can actually be used to enable and disable dwell selection, which can solve the Midas touch problem. Target disambiguation solves the low input precision issue, and also by leveraging eyelid movement, visual depth adjustment solves the difficulty in occluded 3D target selection. So Deep can be applied in engineering, manufacturing, surgery, smart room interactions, anywhere where hands-free interaction and occlusion robots pointing is required. And future works will include developing online AE personalization algorithm, and also testing Deep in the real-world scenarios where there might be more distractions, where you can see the environment around you. And to conclude, the contribution of Deep are we have systematically modeled users' eyelid movement pattern. We propose Deep, which is the first technique to leverage the continuous eyelid movement for visual depth adjustment. And we have also evaluated the interaction performance of Deep. So that concludes my presentation, and I'm happy to answer any questions. Thank you.
Thank you so much. Yep. I see we have a few questions here.
Hello, this is Shun from Purdue University, and thank you for the interesting work. I think I have some questions about the fatigue. Actually, you mentioned in the last part of your research study.
Mm-hmm.
So do you have any get any feedback from the users, after how many times of repeat dwellings will the user feel fatigue, or have you ever considered any improvements to reduce this kind of fatigue?
Thank you. That's a great question. So the fatigue issue, so we have presented several variants of Deep. Specifically here, we have the HDeep, which is the complete set. So we have also developed this location selection where the user doesn't have to select the partially occluded objects with visual, the visual depth adjustment. So that will significantly reduce their feeling of fatigue. And yes, we have collected some subjective feedbacks in terms of quoting from them. And then you can visit our paper for more information on that. Thank you.
Hi, Xin. Thank you so much for the presentation, and I like the novel sampling or novel selection technique.
Thank you.
So my question is as below. We know that the selection technique, the performance of the technique, and the UI layout, and the applications, these three components, they correlate with each other. So I can see that with the accurate performance of your technique, we can create a denser layout because we have a more advanced selection technique. But my question is, I'm curious about the application. Like, under what use cases you recommend, for example, UI designers to design such a dense layout that with occluded target, or do you have any insights on other scenarios we need this technique? Thank you.
Thanks. That's a great question as well. I guess I'm going to answer that in two parts. The first one is, so in terms of UI design, so I think that this can be applied to two types of interfaces. The first one is the traditional like WIMP interface where you might have multiple windows that are overlaid together. And when that is in a VR headset, for example, or an MR headset, then it gets quite clustered. So I guess that our technique is it's definitely going to be helpful in terms of looping through and going through the different windows that are overlapping together. And the next part is, I think, the more important application of this, which is when you're in like a 3D environment and you are viewing a lot of 3D models. Let's say, for example, this example, a surgeon that's conducting a surgery, they have the 3D anatomy of the human body. Or you can probably imagine if you're in a manufacturing setting and you have an engineer with their hands full of tools and they're viewing at the, let's say, a model of the engine. And they probably want to pierce through the model so that they can do through different components and to see, let's say, where the fault is, or they want to just select like very tiny bolts that are in the 3D model. And I think our technique comes in very handy for those applications. Thank you.
Okay, so I think we can take another question while Akar, you can go set up.
I have a very quick question.
Yeah.
So your visual depth selection techniques, does it work only for stereo environments, or do you think it could work for 360 videos too, which might not have stereo?
I'm sorry, can you repeat your question?
Yeah, so the visual depth selection techniques, right? So does it depend on the environment being a stereo VR environment, or can it work on things like 360 videos viewed through VR headsets?
Oh, okay. I think it definitely can, because you can imagine that it's like a sphere that's around you, and then what you're adjusting is not just a planar, but rather a sphere that's around you, and then it changes its radius. Did I miss your question? Sorry.
The sphere is at a constant radius, so like you're seeing a video in which the objects can be occluded.
Oh, you mean when the objects are moving themselves as well?
Correct, like a 360. I can take it offline actually.
Oh, okay. Yeah, that's chat afterwards.
Hopefully
Thank you.
chat during the lunch.
Yeah.
Okay, now we have Akar from Meta Reality Labs presenting his work on RADS. I'll let you take over, Akar.
Right, thanks, Karan. So hi everyone, I am Akar Gupta. I'm a research scientist at Reality Labs Research at Meta. And this is work from our team at RLR. The authors of this paper are Ting Zhang, Zhenhong Hu, myself, Chihao Wu, Hervé Benko, and Tanya Yonker. Ting unfortunately could not travel, so I'll be presenting the work. So continuing the spirit of the previous talk, we'll talk about pointing, and we'll specifically talk about freehand pointing in augmented and virtual reality. Now, freehand pointing is when you are pointing and selecting targets using just your hands without holding a controller or something like that in your hand. And there are multiple methods that have been proposed for sensing these gestures. There's vision-based tracking that's enabled in popular AR/VR devices today, but vision-based tracking can be cumbersome for lightweight headsets like AR glasses. And so there are also wrist-based sensing approaches that have been proposed recently. The problem, though, is that mid-air gesture detection is not as reliable as a controller, right? Vision-based tracking has occlusion issues. Wrist-based sensing can be sensitive to motion artifacts or sensor placements, depending on the kind of sensor they're using. So reliable freehand gesture detection is a problem. And one of the most common gestures here is the pinch selection gesture, where the user marks the selection of the target object by pinching their thumb and finger together. And you can imagine how frustrating it can be if your pinches are not being recognized consistently and there are false positives or false negatives. So how do we solve this? We can, of course, iterate on the sensing methods themselves, right? There's a lot of work that addresses that. What we wanted to do was explore a complementary approach that could remain agnostic to the sensing technique that was being used, but still improve the accuracy of detecting the selection event. So the question that we asked was, can we detect the user's intent to select a target at a given moment using hand motion dynamics that precede the selection event? We call this approach RIDS, real-time implicit detection of selection. It's implicit because we don't use any information pertaining to the pinch gesture itself. We only use hand motion dynamics which precede the selection event. And by hand motion dynamics, we mean the hand position and the orientation information over the course of time. And the way we approach this is to first build a RIDS model purely based on the hand motion dynamics, and then we combine it with the pinch sensing model to get the final probability of selection. And for the pinch sensing, in our case, we use the wrist-based IMU. And what this modular design enables us to do is to have a RIDS model as a separate complementary module that we can train on a task-by-task basis, and then we can combine it with whatever sort of pinch sensing model we have, which is task agnostic. And that will give us the final probability of the selection event. So now let's understand how we build the RIDS model. And first of all, I want to get into sort of what's the intuition here. Why do we think that hand motion dynamics are going to help us decide when a selection event is going to happen? And some of you will be familiar with this graph, this idea that when a user performs point and click, their motion goes through a sort of a predictable velocity pattern, which basically says that before a selection, a user first goes through a ballistic high velocity phase and then a corrective low velocity phase. And so perhaps we can capture some of these dynamics in our RIDS model. But of course, in real world tasks, there are huge variations that depend on a lot of factors. If the user was, let's say, doing a simple Fitts law reciprocal pointing task, then these patterns might be more consistent, but that's not how real world interactions work. And therefore, we chose this task, which is meant to be sort of very realistic. So this is a 1-hour Yahtzee game in VR, and it was nothing like a lab-controlled pointing task. The user had to make decisions and perform selections on different types of objects in real time. And so this made our prediction problem much, much harder, but much more realistic as well. So using this task, we conducted a data collection with 17 participants where hand tracking information was sourced from a puck on the user's wrist, and pinch detection was done using a ground truth finger wearable device. We also collected wrist IMU data that we will use at the end when combining RIDS with the wrist IMU-based pinch model. So once the data was collected, we basically put it through the modeling framework. We extracted the data using sliding windows, sort of the standard technique. So T represents the timestamp here, and we are getting data at every 16 milliseconds. So every frame is sort of 16 milliseconds. The vector that you have here is the hand position and orientation, and a true sample is one which ends with the selection event, so where the label is 1. So for this window, for example, the label is 0 at the end, so this is a null sample. Similarly for this, again, a null sample. And this one, we have a selection at the last frame, so this is a true sample. So we represented the data in this format and then send it off to the model, which is basically a classifier, and generate the RIDS probability of a selection event. Now, of course, we have many, many more null samples here in the data than true samples. So we resampled the data to a fixed ratio of 1:7. The window size was a hyperparameter that we tuned. And for the model itself, the machine learning model, we try out 2 different classifiers. One is a feature-based logistic regression, and the other is a temporal convolutional network. I'll go through each of these one by one. So in feature-based logistic regression, we took a bunch of handcrafted features and fed it through the logistic regression model. We had a huge list of initial features, and we performed recursive feature selection to finally get to 7 final features that we were interested in. And these features captured sort of both the relative dynamics as well as the absolute values or patterns that were observed. Again, without going into too many details, let's look at our modeling results. So these are the results of the leave one subject out cross-validation. So we trained on 16 users and tested on the 17th user, and we did that for all combinations. So this graph shows the precision recall curve. The lines on the graphs represent the testing performance of the held out user, and the thick red line in the graph is the mean curve. So because our data is imbalanced, the area under this PR curve, the PR AUC, is basically a good metric to look at. And this comes out to be 0.355, which is well above the chance of 0.125, but there is definite scope for improvement here. And so we look at the TCN model to see if we can improve the performance even more. And so here we basically feed the hand motion data directly into a 3-layer TCN. And here are the results. So the PR AUC of 0.897 that we obtained here is much, much higher than what we had in logistic regression. So TCN is capturing motion dynamics that our handcrafted features were not able to capture, right? And this is very promising. The figure looks very promising, but I do want to mention that because our data is resampled in that particular way, this does not represent the real-time performance, which we expect to be lower. But it does show that there is definitely some signal here in hand motion dynamics which can potentially improve the detection of a pinch selection gesture. So now that we have a RIDS model, let's go back to our fusion of the 2 probabilities to see if it can actually improve the accuracy of a noisy pinch on the real-time data. So on the top, we have our TCN RIDS model, and on the bottom, we have the RIST IMU-based model. And the RIST IMU-based model was a simple convolutional neural network, which was trained on the IMU data. And we fused the 2 output probabilities using a weighted sum to give us the final probability of a selection event. And this is the final precision and recall. So the blue bars on the left show the precision recall of the RIST IMU-based pinch recognizer, so the RIST IMU-based model only. And the orange bars show that for the pinch recognizer fused with RIDS. And we can see that if we keep the recall relatively constant, we get an 11% improvement in the precision, which basically means a lot fewer false positives with our fused recognizer. Now, of course, these values are pretty low to begin with, so we cannot really deploy this directly in real time. But what this shows is that if we have sort of a pinch recognizer which doesn't have great accuracies, RIDS can make a meaningful improvement in the accuracy of that noisy sensing. the selection gesture. And so in conclusion, RIDS successfully uses implicit hand motion dynamics during pointing to improve detection of the selection event. RIDS is agnostic to input gestures and can be freely applied to other gestures and sensing techniques. And yeah, thank you. Open for questions. My co-author, Janong, is also here and available to answer questions.
Thank you. Really interesting work. I'm wondering, in terms of the improvement that you're getting, how much do the people that you're testing know about the technique that you're using? The same way that if I know about pinches and how to make them, I could try to make them better, right? Can people try to change their hand dynamics to be able to go and help your algorithm do even better than you're seeing?
Yeah, that's a great question. So basically, when people were doing this task, we had them use a ground truth finger wearable device, which was 100% accurate. So they were pretty much doing very light pinches here, because what we used, this finger wearable basically used sort of an electrical approach. And so they were not like trying to modify the pinch in any sort of way, right? We collected the hand motion dynamics and the wrist IMU-based data in the background, but the interaction itself during the data collection was being driven by this ground truth device. So the possibility of them sort of adapting their behavior doesn't arise in this case.
Okay, thank you.
Yeah.
Hi, David Lindenbar, senior, super cool work, Akar. I love the methodology overall. So in
Thank
your
you.
study, you have a kind of artificially large number of events, right? The pinch events essentially every couple of seconds just to train your model. I wonder if you've tested it in a kind of in a scenario where the events are just less frequent, where there's more opportunity for false positives, and how this kind of how much your model really generalizes beyond kind of the setup of your study.
Yeah, that's a great question. I mean, even here, like we did not sort of necessarily make a contrived task to make pinches more frequent, but yeah, I mean it's sort of a game where people are supposed to pinch every few seconds for sure. I think one thing is like the biggest challenge here is sort of balancing the false positives and the false negatives, and like we basically what we did was we resampled our data to sort of this 1:7 ratio, and based on that, we saw that we were getting sort of a very high AUCPR. But then when we actually deploy it in real time, because the ratio is not there anymore, that the whole equation goes haywire. So yeah, I mean I don't have a great answer to this question really. It's just something that I think we'll have to deal with to a certain extent on a task-by-task basis. But yeah, I'm thinking about it as you asked it, and maybe we can talk more offline. Yeah.
All right, great, thank you so much. Well, next we have Yusha presenting her work with Metro at UChicago. This work is really apt. Like something I face on a daily basis is whenever I'm in VR, there are distractions happening around me in my real life. So her work presents a system of how to incorporate these real-world distractions into a virtual reality system and what that looks like.
Checking my audio very quick. Awesome. Awesome. Hi, everyone. My name is Yu Jie, and I am a first-year PhD student at Stanford. So today I'm introducing this work titled Integrating Real-World Distractions into Virtual Reality. So this work was done at University of Chicago during my master's study, advised by Professor Pedro Lopez. So virtual reality enables users to be in an environment beyond their physical presence. With the proliferation of portable VR hardware, we're able now to enjoy the virtual experiences in a less controlled environment. So here, a user is solving a mysterious puzzle in VR in a public game room. Let's see what happened to him.
Did you just turn on the fan? Yeah.
So when users are enjoying virtual experience in less controlled environment, they are usually subject to distractions coming from the physical environment in conflict with the VR content they're consuming, which causes a break in immersion. Well, we can already use things like noise-canceling headphones to block certain kind of noises. Those headphones are only able to block sound up to a certain extent. They don't really work with, for example, multimodal stimuli such as the wind from the fan here, accidental touch, or even smell. So in this work, rather than ignoring or blocking distracting users from VR, we propose a new concept, which is integrating distractions into virtual reality to improve the user sense of presence. So let's watch the same experience again with our concept applied. So here, the sensor box that we prototype attached to the user's headset detects a small set of distractive stimuli such as wind, temperature, and sound. So when a distraction is being detected, our VR experience responds by mapping it to a predefined scene to map the distraction in the physical environment. So here, the wind from the fan was mapped to the movement of the curtain to associate with it. We see our technique to be applied to a wide range of different kinds of distractive stimuli. For example, the sudden sound caused by dropped objects, which could be now mapped to an explosion in the VR scene. Temperature change caused by AC or heaters, as well as long motorized sound from our coffee machines. So how do we know our technique work or how our technique actually has an impact on users' VR experiences? To really understand that, we conducted 3 user studies. And I'm going to talk about the most important one first, which is our in-lab control study. Our first study is purposefully controlled, so we can intentionally create distractions at the same frequency for each participant, and really to understand how adding the distraction integration has an impact on their sense of immersion as well as the perceived distraction level. So we invited participants to the lab and have them play a classic Fruit Ninja game in VR. And for the first study, we introduced 9 distractions in total, which include 4 sound stimuli, 4 haptic stimuli, as well as a smell stimuli. Here I'm going to show you some clips from our actual study of how we created those distractions. So all of the audio stimuli were audio playback from a speaker to the right of the participants. I don't think the sound was working here, but the participants were hearing some laughing sound from the woman for the first demonstration here. All of the wind stimuli were coming from a hand fan. The temperature change, we use a heat lamp. And finally, we create a touch on user's back with a flushy toy on users when I throw on them. As of the mapping we created for this study associated with those distractions, we also propose 2 kind of mapping technique. The first one is what we call direct mapping, where we're trying to create mappings that 100% or like directly trying to map the source of the distractions. For example, laughing from a woman could be coming from like a witch in VR flying by. The accidental touch could be caused by like a fruit bomb on user's back throwing fruits on them. Wind could cause by, or like associate with the swinging of the tree and the visualization of the wind gust. Beyond direct mapping, we also want to offer flexibility of our technique, so we explore what we call stretch mapping, which are mapping not trying to directly 100% map with the distractions, but offer loosely some kind of like mapping to work with it. So this kind of mapping will offer more flexibility for designers when they're designing for mapping for distractions rather than one mapping per distraction. So the laughing sound could come from like a bird flying to the users. Touch could be caused by appearance of bats. And wind, instead of showing actual wind gust, it could be mapped to the appearance of the rings. So here are the full mappings that we designed for the 9 distractions in total we used for the study 1. We run this study with 12 participants, each of them going through the 3 conditions: direct mapping, stretch mapping, as well as baseline, which is wearing the noise canceling headphone only. As of the immersion level, we see direct mapping is significantly better than the other 2 conditions in improving the user's sense of immersion. As of the perceived distractions, we see both direct and stretch mapping are already able to minimize the distractions to its minimal level. Around user preference, so our participants predominantly prefer having distraction integration into VR compared to no integration. So from our first study, we did this proof of concept study to validating our concept work. Now we really want to build up a prototype system to allow us to detect the distractions in real time and automatically trigger the mappings. So we built a prototype system. On the hardware level, we engineered a simple sensing module that allows us to detect a small set of distractive stimuli, such as wind, temperature change, door closing sound, car honing sound, and speech. So specifically, we have a wind sensor for detecting wind and temperature sensor to detect the temperature change. For all audio stimuli, we use a single microphone, which was connected to a laptop on the user's backpack, running dual ubiquitous pipeline for audio classification. Our technical evaluation shows a roughly 80% of detection accuracy across 5 distractions. On the software level, for the designer side, we have a simple script that allows the VR designer to connect their mapping design to the sensor output. On the end user level, we really want to give the users with full control of what they are allowed for integration into their virtual experiences. So before the start of any virtual experience, we present them like a menu and have them to choose what are those distractions they allow for integration. So now we have this system running real time. We want to deploy a real-world environment and to measure users' presence and distraction level as we did for the first study. But this time we really want to have them in an uncontrolled environment, like probably what we use VR for daily. So we used the same VR game, direct mapping this time, and the study was conducted in front of a residential building in Chicago in the winter. So here are some pictures from actual user studies. We see that for the second study, all of the distractions are naturally spontaneous happen in the environment, so none of this is being controlled, and our system detects those distractions and automatically trigger the mappings. Our results with 6 participants showed the trend as we saw in the first study, where having integration of distractions in VR improved the presence level and lowers the perceived distractions. So up until now, I introduced you to this concept of integrating distractions into virtual reality that was able to improve the user's immersion level. But we also have to admit that creating those mappings also require extra effort from our VR content creators. So to really explore this tension, we also conducted a study with 3 VR expert designers by giving them an existing museum scene and a set of distractions stimuli to have them to design around. So here are some final design outputs from the 3 content creators that we studied. All of the 3 content creators found the process of creating mappings for distraction integration to be fun and easy. By interviewing those content creators, we also synthesized a set of design considerations for future designers and researchers looking toward integrating distractions into virtual reality. So today, I introduce you to this new concept of harnessing stimuli that distract us from VR into our benefits. Without any additional hardware, we are already able to deploy our concept in existing VR headset. Most of the current existing VR headset already has microphone embedded, and we can use it to detect noises and have them to be integrated into the virtual experience to improve the sense of immersion. With simple sensor module shown in our work, we can start to detect more complex and multimodal stimuli such as wind and temperature change. When we have more advanced sensor, we can fully expand the concept that we demonstrated in this paper to a wide range of stimuli. We see our work as the first step to exploring the fusion of contradicting sensory experience from the physical world and virtual world. There's a lot of potential to blend the 2 worlds better, and we're excited about it. With that, I'll end my talk here. I'm happy to take any questions.
So I think we only have time to take 2, and also there will be a demo of this work where you can ask Yushin more questions. We can start.
Hi, my name is Nathan. I'm from Carnegie Mellon. Super interesting work, and I think this really does a lot to improve the immersion in VR. One question I have is sort of about like the intensity of these virtual distractions. Like, I'm imagining if I'm doing like a VR escape room and my friend turns on the heat, like if everything suddenly like catches on fire, that's probably super distracting in VR versus like, you know, the sun comes out or a fireplace turns on. So did you think about that at all, sort of the intensity of the virtual distraction and how that might impact the user's experience?
Yeah, absolutely. I think that's a great question. So for this paper, we really focus on proof of concept of if having those distractions to be integrated could be helpful for users' VR immersion. Specifically, how we design those, for example, how they being displayed in the actual VR game is totally up to the control of content creators, how they want to like play around with their existing story. Like as what you're talking about, like a, for example, like a room escape game and a specific theme, the content designers themselves could probably like curate it based on their storyline of their own games.
Thank you for very enlightening talk. I'm Seokang from Postech, South Korea. So my question is the possible coexistence with your approach and safety. So I conjecture that some external stimuli which is not congruent with the VR content may also hearten the user getting alerted about some external physical danger, right? So I just wonder how if you have thought about some possible conflict scenario and some effective solutions.
Yeah, absolutely. So that's why we really want to give users like full control about like what they allow for integration. Currently, we are mostly choosing like neutral stimuli that happen in our daily environment, but doesn't really want to signal like a warning, for example, like fire alarm, stuff like that. Signals like that are definitely not, we're gonna integrate it into VR because we still need to take off the headset and run to save our lives. So definitely we do consider a lot about like ethical consideration behind our concept, and we want to give it like the user full control about like what they allow for integration.
Well, thank you so much. Yep, we can take the rest of the questions offline. And last but not least, we have Akar again presenting his group's work on optimizing the timing of intelligent suggestions in virtual reality.
All right, hi again. So this work was led by Difeng Yu, who was an intern with us at Reality Labs Research. Difeng is a PhD student at University of Melbourne right now. He wasn't able to travel here, but he is online on Discord, so please post your questions in the channel during the talk. The co-authors are Ruta Desai, Ting Zhang, Hervé Benko, Tanya Yonker, and myself. Right, so let's get started. So we'll talk about intelligent suggestions during pointing in VR. And in this figure, the user, you can see, is going towards their desired target. And in the middle of their trajectory, there's a pop-up suggestion. So let me play this again. And the user can sort of select this pop-up suggestion using a button on their controller. And this is an intelligent suggestion where the system shows a suggestion to the user, and then the user sort of uses a shortcut gesture or a controller button to select that. Now, intelligent suggestions in virtual reality can potentially be very useful because the user is doing this effortful mid-air hand motion, especially when the user is searching or navigating to small, faraway objects. And therefore, we've recently seen interest in the building of target prediction models which predict the user's intended target. And the way these models work is that as the user goes through their trajectory, the model keeps updating a probability distribution across the targets in the scene. So that's the thing that you see on the right. So how likely is a particular target to be selected by the user? The selection probabilities sort of reflect that. And the model can use different signals to make the predictions, like the ongoing hand trajectory, the eye gaze fixations, etc. Now, the problem that we are tackling in this work is, when do we make the suggestion? When does the system decide to show the suggestion to the user? So what's happening here is that as the system gathers more signal over the course of the user's trajectory, its predictions get better. And this leads to a fundamental trade-off. If the system gives a suggestion earlier in the trajectory, the suggestion has a lower chance of being accurate. But if it is accurate, then it will save the user a lot of time and effort. If the system gives the suggestion later, it has a higher chance of being accurate. But by that time, it will save much less time and effort for the user. Right? So what's the ideal time to make a suggestion? We need an optimization strategy here to resolve this cost-benefit trade-off. Now, this problem has not really been investigated in a lot of detail in the literature, but there are existing works that have used a sort of heuristic threshold on the model confidence. So for example, when the system has at least an 85% confidence or a 50% confidence in the most probable target, then they show the suggestion. But these thresholds do not take into consideration the user-centric costs and benefits of displaying a suggestion. And therefore, we propose a computational framework to determine the optimal suggestion timing that considers user-centric costs and benefits. So what I'll do next is I'll describe the COBO framework, the cost-benefit optimization framework, first, then the data collection that we did, then the simulation that we did using the data, and finally, our validation user study. Now, the framework basically has two main components. The first one is cost-benefit quantification, where we quantify the cost and benefits to calculate the net gain of displaying a suggestion to the user at any point in time. So what are these benefits and costs? We basically use two quantities. One is the potential time savings or time delayed. So if the system were to show a suggestion at a point in time, what will be the potential time saved or the potential time delayed, because the user may get distracted when a suggestion appears. And the system then uses this cost and benefit to calculate the net gain in time for the user. Now, time is a good metric, but it does not always capture the entire utility of a suggestion to the user. So for example, even if the time savings would have been 0, the user might just prefer to select the suggestion because it's easier for them to do it. It's less mentally and physically taxing, maybe. And so we also use potential usage or non-usage of a suggestion as another sort of objective here that we want to maximize. So basically, the system wants to optimize for the gain, either in terms of time savings or in terms of maximizing the usage of the suggestion. And once the system has an estimate of this gain value at the current time t, the second step, the second component of the system is to decide at what threshold, at what gain value should it display the suggestion. So this graph shows an example gain curve over the course of the user's trajectory. And when the gain reaches this threshold value, that's when the suggestion will be displayed. So how do we determine this gain threshold, the ideal gain threshold? We basically use two approaches. One approach is that for the particular task, we collect user data and figure out a single optimal threshold value. And if the gain of a suggestion exceeds that threshold, then the system will display the suggestion. And we call this approach optimal thresholding, OT. The second approach is a reinforcement learning approach where we say that a single threshold, no matter how optimized, will never work for every single selection. And so we train an RL agent that uses the gain, the progression of the gain over time to figure out whether to display a suggestion or not. So you might be wondering, where do we get the target prediction probabilities from that I showed earlier? And building that model itself is not our primary question in this work. So we use a simulated target prediction model for the purposes of our investigation. So let's move on to the data collection. We do a data collection to figure out the various parameter values that we will use for the cost-benefit quantification. So we collect data on the user's response time, usage percentage, and delay time when intelligent suggestions are displayed at different timings. And we collected the data on two different types of tasks, which are meant to be difficult in different ways. The first one was dense target, which was a physically demanding task with small and faraway targets. That's the thing that you see on the left. And the second one was text matching, which was a mentally demanding task. We also collected data on two different types of suggestions because that could also have an impact on how the user responds. The first one was highlighting, where the system just highlighted the predicted target. So this was a more subtle, less distracting way of letting the user know. The second one was a pop-up notification, which was less subtle. After we did the data collection, we basically had everything we needed to run the simulations, and so that's what we did. And in this phase, we ran the simulations for optimal thresholding to obtain the optimal gain thresholds for the two tasks across two suggestion types separately. And similarly, we trained separate RL agents. Now, in our simulations, we found that the RL agent was performing very similar to the optimal thresholding method. And so for the rest of the talk, I'll focus on the optimal thresholding results. But we did find some very interesting insights in our RL investigation, so please refer to the paper for that. So for the optimization, I mentioned two objectives earlier, maximizing time saved and maximizing suggestion usage. Now, there's no easy way to combine these two objectives into a single one. And so we did multi-objective optimization, where we obtained Pareto optimal designs that optimized for these two objectives. And then we chose basically one of those designs. And these are the final optimal thresholds that the simulation resulted in, and we used them for our validation study. So out of the 4 conditions that we had, two task types and 2 suggestion types, in the interest of time, I'm only showing 2 of them here: dense target with the highlighting suggestion and text matching with a pop-up notification. The table also shows the thresholds that were mentioned in a pointing and a text matching task, respectively, in prior work. And this will form one of the baselines for our validation study. So let's talk about the study. We compared optimal thresholding versus the literature threshold versus no suggestions at all. And we did the study with 26 users. And here are the results. So for the text matching task with the pop-up notification, we see the left graph here basically shows the completion time for the 3 conditions and the right one shows the suggestion usage. And you can see that our optimal threshold method outperformed both the baselines on task completion time and on suggestion usage. Basically, all the differences here are significant. The results for the dense target task with highlighting show that the suggestion usage is fairly similar for the optimal threshold and the literature threshold. The completion time, however, is significantly lower for optimal threshold compared to no suggestion. So takeaways, intelligent suggestion can be useful to reduce input friction in XR. The COBO framework that we propose can be used to determine the optimal timing of intelligent suggestions based on user-centric costs and benefits. And COBO is shown to be empirically effective in maximizing time savings and suggestion usage. And yeah, with that, I'll end. Thank you.
Thank you so much. I think we have time for one question. Someone has a, okay, great.
Thank you for your presentation. It was really interesting. So I'm Songjae from Postech, and I was curious whether your system would robustly work with different form factor objects, and also when objects are overlapping. For example, you're playing a game, making a sandwich, there could be lots of ingredients, and also ingredients overlapping. So I wanted to hear about that. Thank you.
Yeah, that's a great question. So basically, that would depend on, so ultimately, the framework itself can be applied to any scenario. And I imagine the parameters that we tune using our data collection, we'll have to probably tune them on a task-by-task basis. What you mentioned, the scenario that you mentioned where we have occlusion in the 3D scene, I think that's something that's the purview of the target prediction model itself. So if the target prediction model that's generating those probabilities can handle that sort of occlusion, and it can still generate reasonably good target prediction, then great. If not, then it won't work, right? So, so for example, if you're purely, I mean, there has to be a way that the user himself or herself is disambiguating between two targets that are occluding each other, right? And so if there is a way that we can capture that information over the course of the trajectory of the user, maybe using gaze fixations, although they might also overlap, then the target prediction model should be able to capture that nuance. But ultimately, the point is that if the target prediction model is able to capture that, then our framework should be able to develop the optimal timing of the intelligent suggestion. Yeah. Hope that answers your question.
All right, thanks a lot. I won't stand in the way between you all and lunch. Sorry we ran a bit over, but I just want to lastly thank our student volunteers, Rima, Nina, and Violet for helping. And also there's also an XR meetup for folks in this domain I think will be interested in that. That will happen at around 1 at Cascade Room A. So do join in for that. And well, thank you for attending the first session.
I think I don't have audio, actually.
Yeah, let's check your sound thing.
Oh, yeah.
We got it working on Peggy, so.
Yeah.
Can you just go to sound settings?
Oh, yeah? And this one?
Oh, no,
sound setting. Okay.
Like, yeah.
Sound.
Yeah.
Oh, this one.
Okay, we can look at output.
External headphone.
Can you try DisplayPort? Is that possible? Can you try playing?
Let's see. Don't think it's playing.
Okay. I don't know why the external headphones doesn't work, because it feels like that should work.
Maybe, would it be the problem of adapter? Let's try again.
Like, that should be the external headphones, but
Yeah.
But I don't know why it doesn't.
This is my speaker. Yeah. And there is a like empty stuff
Yeah.
here. I don't know what that is.
I think the external headphones should be the right one.
Yeah.
But like, I don't understand why that's not working because this is plugged into the headphone jack, right? But
Oh, is it? It's actually. Oh, should I? Oh, maybe that's the reason. But that's kind of weird.
but this.
That's HDMI.
Yeah, I think we want this. So this is not actually useful.
So it
Okay,
should
so this
go
is
through
useless.
HDMI. The audio should go through HDMI.
Yeah, but you don't have.
Can I? Maybe I can try the other adapter. Like, do you have other?
Oh, there was another one back here.
Oh, here.
But these are microphones.
Oh, these are okay. These are not adapters. Is Peggy still around? Okay. Do you have another adapter? No. Like HDMI, like Type C, yeah, USB-C to HDMI. Because the audio doesn't work.
The audio doesn't work, you say?
Right.
Through HDMI? That might be a...
They worked on Peggy's laptop, so.
Yeah, we use the HDMI
Okay, I'll
port
try
for.
it.
If it doesn't work, just don't worry about it. Just switch the audio to your computer and
Gonna
just
use
direct
mine.
your mic to it.
Yeah, that could work, yeah.
I guess the talk is very audio based, right? So that would be.
That is true.
If we can get this working, that would be good.
Let's see.
Oh wow.
I'm not sure that, actually that's not connected yet, but in theory you could output to this.
Right.
They'll turn on later.
Okay.
There has been a cocktail that I have been dreaming of making recently that I had a...
Try plugging. Okay, let's see.
There has
Oh, it works.
Okay, okay.
So that is the audio input. Okay.
Okay.
Awesome.
Yeah, that's good to know.
This is, usually it goes through HDMI.
Right.
But since it's not, you can just use this for now.
Okay. All right. Thank you.
The only problem is, yeah, it won't go through very well on the stream, on the recording.
Oh, which one? This one?
Maybe that one sounds better. Okay,
one's
yeah.
disconnected
Yeah,
to the
we're
venue.
natural.
Oh,
Yeah,
this is disconnected. Also, it's worse.
This is just directly connected to the venue.
Uh-huh.
So we cannot capture that for the recording.
Oh, maybe I should try, because I think it actually works through HDMI for Peggy. So, Peggy is there. Yeah, Peggy.
Can you move your presentation to her?
To what?
Can you just send her your presentation? It's a Mac, right?
Right.
As long as you're not using fancy fonts.
Right. I'm not.
Yeah, just send her your presentation, maybe.
Okay. Yeah, that could work.
But this is working just as a backup. Is that what you're saying?
That's because the audio doesn't go into the recordings,
Oh,
right? So
I see.
So then it would only capture what this is hearing in that case, which would be, you'll still hear something. but
Right.
It won't be clear.
Peggy, is it possible that I drop my slide to your laptop and use your laptop? Oh, nice. Thank you. Because it doesn't work on my laptop, the audio. And if you use this plugin, it doesn't go through the recording system.
So audio's fine on yours, right?
Yeah, the HDMI one is not working on his laptop,
Yeah.
which is a little concerning.
Oops.
It's also not working on mine for some reason.
Oh, I see.
Brian, do you want to also give it a shot?
Input not support. What does that mean? So it doesn't seem to be seeing my laptop. Yeah, it's not. Yeah, it's not showing up. Oh, alternate version, maybe if I try another port? Or is there more than one? I have maybe a mini, or whatever the heck.
Can I take this one out?
Yeah, go for it. It's weird. I mean, I use this at home, so I don't know. Yeah, this is what I always use.
Yeah.
Maybe. Oh.
Oh, okay.
It changed. Oh! Why didn't that work? I don't care anymore. Exactly. I don't want to ask questions to the void that I don't want to know. So, okay, that's an extra screen. So then in theory, I can just do presenter view, right? And
Drag this one over to the other.
Do you have audio on your slides?
oh, yes.
Test that out as well.
Yeah.
Yeah, let's do that now.
Definitely test that out.
Okay, so that's not playing through HDMI.
I highly doubt it.
Let's find out.
Do you happen to know if the speakers can do spatial sound? Spatial sounds.
Ooh.
Like some sound flying from there.
Yeah, I know, but we just have like.
Yeah.
What if I just play this
I think we have speakers.
Okay, so in theory.
Oh yeah, okay. Yes.
Oh my gosh, it worked. Okay, so the only question is why doesn't this present to that screen? Do I have to push something different to get it to show up on that other screen?
Go to presenter view again.
Presentation and restart. Sometimes that works.
Okay, let's do that.
Stop presenting and then go to it. Are you using PowerPoint or?
So this is Google Slides.
You hit presenter view.
I do presenter
And
view. So let's see if I go to this
can
one
you take
and then
this one and drag it? Can you
yeah,
drag it?
do it. I'm not sure why it's like that. You can
Why can't I
double
drag
tap
it?
Yeah, you can usually double tap the very top.
Huh?
The
How do I?
very top. Yeah, I'm not sure.
Oh,
why
up
it's like
there.
that.
Oh, okay.
Yeah,
Okay.
it's Google. I mean, not Google. It's Lens.
Is that the adapter I left here?
That one's mine. Is that the one you need?
This one?
Maybe?
This is yours. This is hers.
Maybe it's just being silly.
Yeah, can you try dragging it to the other window?
Yeah, where the heck is the
Why
other
can't
window?
I drag it?
Is it off the
Okay,
right?
here.
Oh, there it is. Haha.
Okay.
Okay,
But no
so-
sound is going, so that's good.
Do you still need to test your sound?
Yes. Well, I'm the session chair,
Yeah,
so
no,
I'll
but
just
you're
test.
doing the lighting test.
Yeah.
Oh yes, are you about to have another session, or are they just getting you?
Huh? No, for our session, I need to play the lightning talk in the beginning.
Oh, got you. So you need to test your thing next.
I still have another presenter who
Where's the
hasn't
mouse?
had a chance to test. Is that okay?
Okay, cool. All right, so that worked. So in theory, I just unplug.
It's right there, but yeah.
Okay. So I'll just unplug, and fingers crossed that it continues to work.
Yeah, I hope so.
Specifically, I am interested.
Of course. Where did the sound thing go? Okay.
Using human.
Making all the other laptops work gives me some breath. Thank you for your help. Okay. Oh, I see. Cool. We'll just get started now then. Welcome to the storytelling and presentation session. I'm Jane E. I'm currently a postdoc at UCSD with Stephen Down Haijinxia, and I'll be your chair for this session today. So we'll be starting with this lightning talk, and then we'll have 6 papers presenting. we have our presenters sitting here now. So for each presentation, we'll have around 12 minutes for the talk, and then unfortunately only 2 minutes for Q&A. So I'll try to keep it to sort of like 1 or 2 questions per talk, but the presenters will all be here after for more, just to try to keep us on track. Yeah, and so for people who have in-person questions, please come up to the mic, and when you're asking your question, if you could just state your name and affiliation, that would be great. And then our SVs will be sort of helping to monitor the Discord as well for any online questions. And yeah, so I'll just get this started.
Hi, my name is Jian. I am an undergraduate student from the University of Calgary, supervised by Dr. Ryo Suzuki. And my research interest lies at the intersections of human-computer interaction, mixed reality, and natural language processing. Specifically, I am interested in using human-centered design to empower the mixed reality applications with multimodality and establish a more immersive AI-driven computing system. An example is my recent work, Reality Talk, that can augment live presentations with speech-driven interactive virtual elements. Meanwhile, I'm also part of the Entrepreneur First TO4 cohort, and I'm hoping to turn my research ideas into commercialized real-world products, which focus on the future of work and augmenting communication through human-AI interaction. Finally, I am here to find research and industry opportunities, as well as potential collaborators to work on some exciting projects together. Thank you.
Okay. I'll let you sort of set up and move away so that you have that. Cool. So our first presenter is Sang-Hosa. So he did this work while at University of Waterloo, but recently joined us at UCSD. So I've still somehow only managed to actually see him in person here at conferences. But maybe I can help with. Hopefully it just works. Yours seem to be the most smooth overall, so and feel free to adjust the mic if you want to. Do you need internet? Okay.
Yeah, I think it.
That seems good. Okay. Perfect.
Where's the HDMI? HDMI? Oh, this one? Oh. Oh, here.
I thought it looked like you were ready. Just wait 1 second. It doesn't look like it actually reacted. Sorry. Oh, now it looks like it's doing something. Like your screen looks like it at least reacted to something. No, it didn't work. I don't know. Yeah, it worked earlier. Yours was the only one that worked smoothly earlier. It's not working again for some reason. It could. Do you need this for something?
Yeah,
you do, right? Let's just try this one more time. It was fine. It just does feel a little loose, so.
For did you try with like?
It looks so full. No.
Or did you try different holes? Like
They're only the two. Oh.
Oh, I think
Nice.
like you need some pressure here.
I see, I see.
So like put something like.
Yeah, it does feel a little loose, the connection. We could possibly. That feels, yeah, okay. I'm going to try to use this one, okay? I'm going to plug yours into this. Okay. You good?
All right. Thank you for waiting. Thankfully, it's still not the start time. All right. Hello, everyone. So, as Jane said, I'm a postdoc at UCSD Design Lab. But this is a work I've done during my PhD with Jen Zhao and my advisor, Edith Law, at the University of Waterloo. So here's a picture of two kids looking at a laptop screen. Does anyone find anything weird about in this picture? Well, I think it's weird that they are looking at just this Java code and are smiling, because I don't know how realistic this is in real life. And this is because we all know that making programming engaging and interesting is very difficult, right? And this is because programming requires learning abstract programming concepts, languages, and procedures. And to address this and to make programming more accessible, there has been a lot of research, right? From developing programming languages that leverage physical, concrete representations to using simplified text commands and visualization, among many others. So at the core, these research, along with the research I'm presenting today, all tackle this question of how should we teach programming? Or more broadly, how should we teach computational thinking? But what is computational thinking? Well, computational thinking is commonly defined as this ability to rapidly shift levels of abstraction, seeing things in the large and in the small. And this is because computer scientists need to work with many levels of abstraction, when they're learning or dealing with frameworks or technology stack in programming, networking, or operating system, and many more. And being able to change levels of abstraction is also very critical when learning programming. So for instance, when we're learning programming concepts such as recursion, we often use analogies or real-life examples to contextualize and make sense of them. And also when learning programming language, its semantics and its syntax, which seem very arbitrary, it is very useful to relate that to natural language, which we are already familiar with, and even connect them to visual language. And also when learning programming procedures such as loop, we need to go beyond and deeper into its abstraction and actually explore different execution steps to learn how to trace them. But unfortunately, instructions in computing often tend to be stuck in abstract levels of abstraction. And without moving up and down. So, and although it is done to some extent through verbal or visual explanations, or even the tools that I've shown at the beginning, and I think there should be a greater emphasis on being aware of these levels, because I think that thinking explicitly about these levels so that we can move between them is key to making programming more engaging, accessible, and interesting. So to this end, I have previously proposed this idea of coding strip, a form of comic strip with its corresponding code, so that we can think explicitly about these levels and move between them. And the reason for using comics is because it is an incredibly powerful medium, not just for storytelling, but also expressing computational concepts, languages, and procedures. So as I said, when learning concept, we use stories, and stories can be embedded in comics. And also when learning language, comics, the visual language of comics can complement and help make sense of seemingly arbitrary syntax and semantics. Also when it's effective when it comes to illustrating procedures, because it can leverage panels.
And it's also very flexible and expressive. It can express anything from abstract data structures to linear and nonlinear procedures. So I demonstrated this in my prior work where I explored design patterns, design space. And I also found that although both teachers and students are very excited about using CodingStrip, this laborious and time-consuming nature of creating CodingStrip poses a barrier to its adoption. So this motivated us to study how we can maybe automatically generate comics, and this led to the development of CodeToon. And CodeToon does this by first guiding users to define a story based on the code, and then it instantly generates comics from the story. And this storytelling process driven by code is embedded in the interface. So let's see a quick demo to see how this works. So you can add code either by just typing or selecting any of the code examples, and you generate a story template on which you add story. And as you can see, there are metaphor suggestions for variable and operators to help you brainstorm story ideas. And after you have a story, with a click of a button, you can instantly generate comics like this. And you can edit it however you want. You can customize it. You can add color, different strokes, and so on. So you can be more creative. So you don't have to be stuck with this. And you can also add predefined comic templates to further enrich your comic and story. But the important question also is this useful, right? Or how can it actually facilitate teaching and learning? So I want to just share some examples of how it can facilitate teaching and learning of concept, language, and procedure. So first concept, I think when learning abstract concepts, as students always say, oh, I want more examples, right? And this is possible in CodeToon because updating comic is instant, it's easy. You can just change the story and you can update it. And this allows teachers to also explore different analogies or metaphors they can use to explain. And maybe teachers can invite students to and offer some story ideas that may be relevant to their personal experiences, right? So this could make the whole learning process more engaging and interesting. And with language, this is just one example. So CodeToon, we use Python as the basics. And the design, the visual grammar basically was used to kind of, this one in particular, it tries to emphasize the indentation, right? So in Python, this is important. If you have the wrong indentation, you get an error, right? So we use this empty gray panel to highlight this, right? So this can be used to explain the syntax. Also for procedure, so actually CodeToon uses an actual parser in the backend, so it actually computes. So here, you can edit the code however you want, and then based on that, it can show each execution step. So teachers can maybe show and then explicitly say, oh, so this is what the values are in the second iteration, third iteration, and so forth. Students can also use this to test their understanding, just to check, whether they're understanding, whether they have, fully understood, right? And I also want to highlight that the visual grammar that I talked about was designed with the whole purpose, with the intention to kind of make the execution steps visible. So what do I mean by that? So variable assignment at a low level, right, occurs in two steps. You create memory space and then you assign the value, right? So this is actually manifested by having two panels. This first panel is supposed to represent creating the space and then assigning the value. So teachers can use this to point out that, hey, by the way, at a memory level, this is what happens, right? And one design goal that we focused on that I want to share is making the connections between these code, story, and comic clear and explicit. Because when using multiple representations, making the connections clear is very important, because otherwise it just confuses you, right? So what we did was basically there's one-to-one mapping between code and story. So for instance, each line of the code maps to each line of the story, as you can see there. And also, this one-to-one mapping carries over to the mapping between story and comic. So this was to really help, maybe let's say students, right? When they look at the comic, they can instantly know which line the comic is referring to. So to evaluate this design choice and code tune, we conducted 2 comparative studies. The baseline system looked exactly the same as code tune, but just didn't have the metaphor suggestions or the auto comic generation features. So they had to manually come up with the stories and comics. And in the user study, we had them generate coding strips. And then in the comic evaluation study, we had other group of people evaluate the quality of these comics generated by baseline and coding users. And these are just some examples of baseline comics. And as you can see, the design language varies from participant to participant. And you might notice the lack of these panels to use of the panels to kind of impose the structure. Right? Whereas with coding comics, because they had this system automatically generate comics and it mapped to the line of the codes, it was much longer and more structured. And so this code is about how it helped them save the time, and also all they had to do was just add details. So we did inform participants that they can edit. They don't have to use the auto-generated layout or comic, but they still, all of them did, and then said that they just have to add details because they were satisfied with it. And another quote was about how accurate the mapping was. And interestingly, this person, and actually several participants, acknowledged that they didn't know how comic can be this useful when teaching programming. They had this preconceived notion that, okay, well, they're probably going to just use comics to narrate programming, but they were pretty surprised and that they supported the whole mapping. And also interestingly, there's a lot of use of metaphors in CS education, but they also said, this kind of helps address the inaccuracy. So key takeaways, CodeTune helps create high quality coding strips in a shorter amount of time, and CodeTune and its comics are seen as useful, and one-to-one mapping can be a very useful design guideline when you're using comics. And as we wrap up, I want to end with what really excites me moving forward and about this work. So while this was about programming, I think many technical domains, such as those listed here, can also benefit from using comics because they also face the same challenge of, explaining and communicating abstract concepts or language and procedures in their respective domains. And as you might know, there are already a lot of work on data comics, but I don't think there's a way for them to generate comics directly from data, right? And I think it would be really amazing to have, let's say, I think actually it touches on Ted Chiang's keynote comments, where he talked about, can we have a discourse based on mathematical equations? I think this might be a really interesting thing to explore too, and I hope to see more examples of this in the future. With that said, I'll be doing the demo of CodeTune this evening, so if you're interested, please stop by. If you're interested in learning more about the research and coding strip, here's the link to the website, so please feel free to visit, and thank you for your attention.
Yeah, feel free to come up to the mic to ask any questions.
Thank you for very interesting talk. I'm from Postec. So my question is about diversification. So I believe that the people like comics, but they don't like reading the same comics again and again. And then when they program, then there are same pattern appears again. So I just wonder if you're supposed to support such diversification in the same article.
Right. Yeah, thank you for the question. Yeah, that's a good question. So it does not at the moment, or when we did the study, but that was definitely one of the comments that came up, such as supporting different design patterns, design language. So yeah, definitely that's something we hope to do. And there are a lot of different design patterns we could utilize too, like whether if for loop, right? Do we want to show all the steps, right? If it's repeating 100 times, you don't want to do that. So sometimes you might want to do one-to-many, many-to-one mapping and things like that. So that would be kind of one of the ways we can change and allow users to select and just explore different designs, for their purpose. Thank you. Yeah.
And now
Yeah, thank you. Great question. Yes, definitely interactivity. I think it will be something we need to add in order to be able to really work with the complexities, right? And yeah, like scalability. Like, can we scale, right? Like, because the one-to-one mapping right now requires that if you input this long code, right? You're gonna have this huge, comic, and maybe it's probably better if we can find a way to abstract that, right? But if they want to explore deeper, like, let's say like with the function level, right, we can abstract it and present it as an abstraction. But then, with the interactivity, maybe they can click and then look at each step if they want to learn more about each step. So I think that would be a great direction to go.
Let's thank Sama again for his talk. Sorry for all those technical things that happened. Let's hopefully. Okay, we're hoping that we
have this audio working. Yeah.
This is the.
Okay. Oh.
Okay, so our next talk is by Brian Wang from University of Toronto. Brian will be presenting his work on automatically generating shortened versions of audio stories. And hopefully we'll get this up and running easily. Yes, nice.
Yeah, fingers crossed. All right, good afternoon, everyone. Happy Halloween. So my name is Brian Wang from the University of Toronto. And in the next 12 minutes, I'll be introducing you Record Once, Post Everywhere, or ROPE, automatic shortening of audio stories for social media. And this work was done with my amazing mentors, So Eugene and Gautam Mysore from the Adobe Research Group at Audio Research Group at Adobe Research. So before I get started, I would like to do a quick poll. Please raise your hand if you ever posted on social media before. All right, almost everyone, right? And please keep your hands raised if you ever run into these situations where the content you try to post is too long and you have to trim it a little bit before you can publish it. Still quite a lot. Well, thank you for your participation. And trust me, you are not alone. Over the past few years, short-form media has become, such as TikTok's videos, has become extremely popular. However, these platforms tend to have length constraints on the content. For example, 30 seconds for video. And if your initial content is like 50 seconds, shorten it to 30 seconds is just difficult. And creators usually have to create multiple versions of the same content if they want to publish on different platforms, which can be tedious. On the other hand, since the pandemic, social audio, such as Clubhouse, has emerged as a new type of platforms where people share their stories through audio. Tech companies have also started to build social platforms that allows users to upload their audio recordings, sort of like the audio version of Instagram and TikTok. However, audio editing is already challenging enough for novice users, not to mention to make sure the content complies with variable length limits. So in this paper, we investigate how can we make short-form social audio creation easier. And to achieve so, we present ROPE, an intelligent system that shortens speech recordings to any given length limits by automatically selecting sentences from the input audio. Oops, sorry. So the user only needs to focus on generating content, and the ROPE will use natural language processing to figure out what parts to remove with minimal effects to the storyline. So let's do a walkthrough on how user can create short audio stories using ROPE. First, record. The user can record a short speech on any topic with any device without worrying about the exact timing. They can specify the target length of the audio to ROPE. Let's say we're posting to a platform that has a limit of 30 seconds. Next, ROPE will process the raw recording uploaded by the user and retarget the audio length to the specified 30 seconds. So if the user is satisfied with this automatic output, it's good to go for publishing. And if not, they can use the ROPE user interface to refine the algorithm output. We provide two different editing paradigms for refining the output. First, the ROPE toggle allows users to click on each sentence to include or exclude it in the output audio. And the total length of the output audio will be reflected in the progress bar down below. so the user can use it to ensure that the audio is within the length limit. The second paradigm is called rope recompute, which allows users to specify the most and the least important sentences in the story, and the system will automatically recompute a new version that complies with the specified length constraint. So now, why don't we listen to an audio example created in our user study? It's a 71-second story on a tasty cocktail, and the rope shortened it to 30 seconds. And let's hope the audio works.
There has been a cocktail that I have been dreaming of making recently that I had a while back called the Division Bell. And the Division Bell is delicious. It is a mezcal cocktail. It has mezcal, Aperol, lime juice, and a maraschino cherry liqueur, which is surprisingly hard to find. And it's amazing. It's fruity, it's smoky, and it's a cocktail that doesn't taste like anything I've had ever had before or had since.
So this short story is compact and self-contained. It says Division Bell is delicious and talks about what ingredients does it have. Compared with the original story that a user recorded, you'll find that rope removes the parts that go into details about the mixologist in New York City and where to buy the maraschino liquor and how to mix it. But the overall storyline is preserved. So in this example, all the great sentences were edited by rope, and the only user refinement was the orange sentence here in New York City. Now let's talk about how we built rope. We designed a system based on our formative study findings with Amazon Mechanical Turk. Our first study shows that the audio stories that people record share a common topic-based structure, and it is possible to remove one or more topics without affecting the overall storyline. Our second study aims to understand the limitation of speeding up, which is a common approach that people use to shorten audio or video currently. And we found that using speed up to shorten audio wouldn't work well if we want to shorten the content to let's say, half of the original length. It will need to be sped up to 200% faster, and that will generate significant sound artifacts. So an alternative shortening method is required. And these findings motivated the rope algorithm design. The core idea behind rope is that we formulate audio shortening as a combinatorial optimization problem. That is, given the audio story on the left, our goal is to select an optimal sentence subset whose total length is equal or less than the specified limit. So in this case, 45 seconds, 30 seconds, and 15 seconds. Let's take a look at the whole picture. Rope first transcribes an audio story into a text. It then segments the text into sentences. It uses abstractive summarization to obtain an audio story summary. Next, it calculates the sentence scores according to the summary, which we will discuss later, then uses dynamic programming to find out the optimal sentence selection with complying with the length constraints. Lastly, it generates the output audio based on the selected sentences. Let's zoom in a bit into this optimization process. So given an audio story, we first split the transcripts into sentences and extract each sentence's audio. So this will already remove excessive silences between sentences in audio. Next, we compute the story summary using a BART-based summarization model and split the summary into sentences, which we consider as topics in the story. Then we calculate the sentence scores based on our score function, which indicates how relevant a story sentence is to each topic in the summary. We then use dynamic programming to select sentences that maximize the total score while the total length is no longer than the limit. So it's pretty much equivalent to the classic 0-1 knapsack problem that you probably have learned during the undergrad algorithm course. But how are the sentence scores calculated? Given sentences in an audio story and its summary sentences, we project the sentences to the sentence per embedding space. We then calculate pairwise cosine distance between the embedding of each sentence in the story and the summary. Our score function considers how close the story sentence is to each summary sentence. The smaller the distance, the higher the score is. It also considers each sentence duration in audio, and longer sentences get higher scores because we want to encourage the algorithm to favor more complete sentences. So please refer to a paper for more details. In a user study, we compared using rope to shorten audio stories with manual editing. And the key takeaways are that the automatic output from rope is already equally satisfying with those created with manual editing, but requires no user effort. And if the user further wants to refine the automatic output, it actually leads to a greater outcome satisfaction. Now let's talk about the limitations and future work for rope. Firstly, our algorithm depends on speech to text, which can be sometimes inaccurate due to accents or audio quality. So as the technology improves, rope's performance will also be boosted. Secondly, rope operates on sentence level, yet sentence segmentation of speech can be imperfect, as it also relies on transcripts. On the other hand, while sentence editing is fast, it does not support more fine-grained control, such as editing individual words. And however, removing words in speech without generating artifacts remains an ongoing research problem in the audio processing community. So future work can incorporate more advanced speech synthesis techniques to address this problem. Third, rope used abstracted summarization, which may omit some subtopics in a story. Therefore, these topics will be less favored by our algorithm, and future work could explore more steerable summarization techniques for better user control. While we initially developed rope for audio story editing, we found that it can actually work some videos that are narration heavy. So here's an example of shortening a 60-second TikTok video to 30 seconds.
Today in Tokyo, we found these magic singing pills. We had to take them to karaoke to try them out. Karaoke is extra in Japan. There are a variety of song choices, and you can even score yourself as a challenge. We got takoyaki and nugs, but it's time to put the pills to the test. Maya played the challenge mode to keep a score on her singing. There's a gauge throughout the song that helps keep score. The pills take about 15 minutes to kick in, and they're supposed to loosen your vocal cords, so she sang How Far I'll Go, and she ended up scoring an 85. We waited a while, and we did a round 2 with the same song, and she ended up scoring even higher.
So if you compare with the original video, the main story is preserved. The story is about taking the singing pills and go to karaoke to sing songs. But the details about the karaoke itself and how you order food and drinks were removed, as well as the last 2 sentences asking viewers to try the pills out. And due to the time constraints of the talk, I cannot play the original video. However, I do encourage you to check out the demos on our project website. We open source the audio recordings that we collected in the formative study for future work to build upon them. And the link can be found in the paper. Lastly, a future opportunity in this area is to support screen-free audio creation and consumption so that users can interact with audio content without looking at the screen. And this could be done with recent advances in language modeling. For example, users can use free-form language to navigate to a certain part of the audio and edit it. And with that, I wrap up the talk, and I'm happy to answer any questions you have. Thank you.
Thank you for a great talk. It was very interesting. And I have a question about the summary of from the GPT-3. So you said that you calculate the similarity between the summaries and each sentence to find the important sentence in the story. But actually, sometimes if you miss some sentence with some conjunction, or then it seems like it is not logically similar at all. Or sometimes, for example, if you extract the sentence before the sentence with thus or therefore, then it seems like, oh, so where is the cause? Where is the effect? Or where is the result? That kind of thing happens. So
right.
How about what I want to ask about that. Your opinion about that problem, and I also wonder if I'm curious that how GPT-3 is
can make the summary logically. I don't know. Never mind about that that question.
Right.
Thank you.
Right. Thanks for your question. So for the first question, yeah, that could be a problem. Like if sometimes you remove part of the story and it turns out the logic doesn't make sense, right? So that could be a limitation of our current implementation because we do not have any mechanism to check the logic. So yeah, that's one of the limitations we have, but also that's why we have this user in the loop refinement, so that those cases are not very common. When they do occur, users have the control to refine them, so to ensure that the overall story flow is still logical. And for your second question, we actually didn't use GPT-3, but we can talk about that later, after the talk. Yeah, thank you so much.
If you could try to keep the questions a little quicker, and then maybe if we can just start setting up so we can do those simultaneously.
Thanks for the great talk. It's
Thank
really
you.
interesting and cool technology. I was just wondering, did you test any conversations with two people or more than one person telling a story, or maybe something like a conversation between two people, or is that something that you might do in the future?
Right. Yeah, that's a great point. In this work, we only consider a single person speaking in that audio, so the algorithm is designed based on this assumption. And to generalize, I definitely see potential to generalize to multi-party conversation, but that would require more investigation to characterizing the data set and building model or algorithm surrounding that. But yeah, that is definitely the next step for us to do. Thank you.
Hi, David Denver, CMU.
Hi.
Super cool work. I was wondering, have you tested the limits in terms of length? Could you use a 1 hour audio and trim it down to 30 seconds, or would it just explode combinatorially?
Right. Yeah, that's a great question. So in this work, we focus on short form audio, so it's more or less around 1 minute or to 2 minutes. But I'm not sure how much I can say, but we're actually testing it on longer audio, and that's something we're working on, and that's definitely something interesting. Yeah, thank you.
Okay, thank you all for bearing with all the technical things and trying to hurry up with the questions. But our next speaker is Rachel Cheng from University of Michigan, who will be describing OmniScribe, a tool for authoring audio descriptions for 360 videos.
Thanks for your introduction. Hi everyone, my name is Rachel Chen. I'm a first-year PhD student from University of Michigan. Today I'm going to tell you about OmniScribe, a system that makes 360-degree videos accessible to blind or visually impaired people. This work was done with my collaborators Zhao Xianding, Jiasheng Hong, Wanzhen Li, Liangjing Chen, and our collaborator in Audio Description Development Association, Youci Zhao, as well as my advisors, Bingyu Chen and Anhong Guo. First, let me show you a typical video.
Go to class. Run in Asia. Get your instruments, have a seat.
For blind users, they may access this video augmented by audio descriptions, which sounds like this.
For a hug. Go to class. Run in Asia.
She greets two girls, students in a band room.
Get your instruments, have a seat.
A student holds a tuba. Others play a flute and a clarinet.
This is how audio descriptions work. Now mapping videos onto this spectrum, I just show you 2D videos that can be augmented through audio descriptions. But how about 360 videos? The omnidirectional nature of 360 videos introduces several challenges and opportunities. For describers, it is challenging to understand extensive information, such as their direction and movement airtime. For blind people, it is also challenging to use standard audio descriptions to get a sense of immersion. In our work, we aim to answer an overarching question: how to make 360 videos accessible. which includes how to support describers to describe 360 videos, and how blind people can consume the descriptions of 360 videos. And that's what OmniScribe aims to address. Let me give you a preview of how blind users will consume 360 videos.
Several elephants are at the Elephant Sanctuary water pool, and one of them is raising its nose and slapping the camera, which ends up blocking the entire screen.
So the speaker cannot render stereo sound, but you can think about the audio description is specialized on your right in normal cases. Yeah. So blind people can also access additional extended descriptions.
It is the baby elephant closest to you. It has a long, wrinkled trunk, and it uses the nose to push down the camera you are looking at.
Yeah, so the sound should be on your right. Overall, OmniScribe includes a web author interface for describers to author immersive audio descriptions, as well as a mobile prototype for blind people to consume the generated audio descriptions. To understand the challenges and needs, we got deep insight through a series of interviews with a professional describer who has over 20 years audio description experience. We identified 4 design goals, such as we should facilitate the 360 content understanding, provide conceivable information to help blind people construct their mental model for the video, and enable immersive audio description authoring, and also the tool should be easy to learn and use for all population. This is the OmniScribe web author interface, which includes a description authoring panel and a timeline panel for video navigation. It also has an equirectangular view to provide global information, and amend the separation of the left and right boundaries. It also provides a more field view of the video. And both of these video views include view control widgets that allow users to pan the video. The system architecture of OmniScribe looks like this. It uses a video processor to generate a variety of data to the web author interface. It has a description processor to generate audio file and a thumbnail processor to generate thumbnails for video frames and objects. OmniScribe uses several overlays to increase content awareness, including section division overlay to help distinguish visual sections. It also uses object tracking overlay to provide visual cues for users to observe and follow specific objects. As well as the CDNC overlay to enhance the contour of salient objects. We also present a content map to visualize the detected objects in a circular map. When users click on the individual icon, the video will be automatically adjusted. To author spatial audio description, the describer can first highlight the text and click on the highlighted text and select the label path on the prompt. The describer can use the brushing tool to pan the sound path on the equirectangular view.
A group of baby elephants is running towards the elephant house.
OmniScribe then transforms this 2D path into 3D spherical coordinates, which can be rendered spatially to the user.
Breakfast, of course.
A group of baby elephants is running towards the elephant house.
So the sound should be from left to right on your back. Yeah. To let blind people understand the new scene, OmniScribe preempts a description slot for each scene, allowing the describer to detail them. It also enables the describers to select objects and describe, and the sound path of object will be pre-populated through object tracking.
An African female elephant keeper dressed in green is moving multiple plastic boxes with formula for different elephants from one refrigerator to another.
So the sound should be on your right. To first evaluate our web author interface, we conducted an evaluation with 3 professional and 8 novice describers, where they described 2 videos with varying levels of narration. They used OmniScribe as well as a baseline interface that only had the subset of OmniScribe functionalities, just like other commercial video editing tools. Overall, OmniScribe provides more directional and conceivable information for describers to observe and select content to describe, such as they can more easily observe many objects and their directions in complex scenes. However, we also found that professional describers struggle with the trade-offs between blind desired content and directional information, which is unique to 360 videos. As one professional describer said, I was trading off between directional information and blind desired content, like the girl with blonde hair or blue eyes. It's hard to describe them all in time. This also makes professional describers to rethink the responsibilities between describers and video creators. As one professional describer said, I found describing 360 video has transformed my role of describer into a director who should decide a storyline for audience. Future work can explore how to convey video creators' intent to describers. So I just showed you the web author interface. Now let me show how blind users will access the generated descriptions through our mobile prototype, such as for this video.
Standing right in the middle of Kenya's first community-run elephant sanctuary.
Here is a savanna. The elephant house is on the left front.
Home to orphaned baby elephants.
And a jeep is entering the elephant sanctuary.
So the spatial audio description is rendered in between video narration and presenting spatially. The sound should be on your right. Left, sorry. Blind user can also access extended scene descriptions.
Now you're back to the elephant square. The keepers are feeding the baby elephants with formula milk.
Blind user can also explore the object description by orienting themselves around.
A baby elephant, waist high as an adult, is drinking milk from an elephant keeper from a white plastic jar that has just been filled with formula milk. The keeper is feeding the baby elephant. The elephant raises its trunk to the keeper's face in front of it. The keeper is feeding the baby elephant.
To evaluate this mobile prototype, we conducted another study with 8 blind participants. And users found that spatial, scene, and object description can provide more sense of immersion and improve accessibility of 360 videos. However, we also found the trade-offs between the immersion and cognitive load. As one blind participant said, it was tiring to interpret the direction of the description, like there is an additional layer of information imposed on me to understand. To summarize, OmniScribe uses a human AI pipeline to make 360 videos accessible. For describers, OmniScribe highlights important information and enables the authoring of immersive audio descriptions. For blind people, OmniScribe presents audio descriptions spatially and responsive to user, which provides more immersive and interactive experience. Now coming back to this diagram, OmniScribe represents an important step towards making 360 videos accessible. If we add time dimension, the OmniScribe approach could also be extended to other immersive media, such as 360 images or VR scenes. And for 2D videos, OmniScribe could also help make them more immersive and informative. Thanks for your attention. I'm open to questions.
Hi, thanks for a great talk. My question is like, when you watch when blind people watch the 360 videos, how to decide when to trigger out the description? As also, the video is dynamic, right? When you rotate, for example, to the right, probably something has already changed. Will you pause the video, or how do you handle it?
Oh, yeah, so there are 2 types of audio descriptions. So one is inline audio description, and the other one is extended descriptions. So the inline descriptions is feed into the video gap in between the narration. So blind people can just listen to these inline audio descriptions when watching the video. And if they want to access like the scene description or object description, they will pause the video to access the extended descriptions. so they can turn around themselves to facing the objects, and there will be an object description play out. Yeah, this is how our these three audio descriptions work.
So it's going to be like when you face the object, and then it will trigger out the object audio description.
Yes.
But if you touch that object, and then it will not, right? This kind of like you will set up a threshold for the behavior.
Yeah, we set out a threshold like so we track their orientation based on the gyroscope of the headphone. So yeah, we have their orientation data, and we have a threshold. Yeah.
Hello. Yeah, thank you for the interesting topics, and this is Shin from Purdue University. Yeah, actually, I have a question about like in the use cases you showed. Most of them are focused more on the object in the front end of the entire scene. But I was wondering, like, are you able to, for example, I'm also interested in like the entire environment. For example, at the back end, you also have the mountains, and you also have some trees at the back end. So have you considered those objects, or you only focus more on the elephants and deers?
Oh, yeah, thank you for your question. So basically, in our interface, we just try to like make objects salient and observable for describers, and describers will choose whether to describe those objects by themselves. So it's kind of like, yeah, decided by themselves instead of our system. Yeah.
So you mean the describer can also, for example, like describe the entire, like the mountain there. For example, like when I turn left and right, well, the mountain are always there, right?
Yeah.
And at the same time, maybe at some moment there's an elephant in front of it. Then you mean the describer has the freedom to like have both of them?
Yes. Yeah, describer has freedom to author anything in our interface.
Okay, let's thank our speaker again. Okay, so our next talk will be by Peggy Chi from Google Research, who will be describing their tool for prototyping videos through interactive scripting.
If you fails, then I will check. Like, I will also count the time here. Okay. All right. Hello, everyone. This is Peggy Chi from Google Research. I'll present a video prototyping approach given a tutorial document with the support of synthetic videos. And this is a joint work between Google Research and Flutter. Okay. The internet contains a vast amount of learning resources. For example, to learn a new programming language, people may look for video tutorials on YouTube to have an instructor to guide through concepts and code examples. But meanwhile, learners may also look for text tutorials, especially to follow code snippets and test in an IDE. However, instructors may not necessarily have sufficient time and expertise in production for different presentations. For programming especially, it is common to just write a text-based tutorial, and we're wondering how can we actually automate the video creation process from documents. At UIST 2020, we introduced a method that converts a web page into a short video that maintains the assets and visual design. And last year at UIST, we presented another method that converts text and visual assets from a tutorial into a longer video with a text-to-speech voiceover for test following. Now, one of the challenges for programming tutorials is that there are limited visual assets. To support this, we're inspired by existing videos that are often led by an instructor. They're walking through the code, examples, and the concepts. So in this work, we propose a video prototyping approach that automatically converts a tutorial document to a script with a preview of synthetic talking head videos. And based on the document content, we suggest scenes and narrations and automatically render a virtual instructor placed in different layouts to present the document content. And we focus on video prototyping by presenting a pre-edited script with scene breakdowns, video previews, and the talk script mapped to the source document. In this way, our goal is to really help creators to jumpstart their creation process and focus on planning the instructional content while they can later on go to record in the next phase. So let me go through our user interface. In our UI, each role represents a scene mapped to the source document, such as the title, a paragraph, or code snippet. And there are three components in a role. First one is the content from the source document. The second is the talk script for the creator to read out. And the third one is a video preview that shows the visual elements and a synthesized talking head video in a graphical layout. And here in this example, it converts the tutorial title to the opening scene. And our pipeline adds a sentence to the title just for connection. So it adds, in this tutorial, we'll learn how to, and followed by the text title. And the UI also shows the estimated duration from a TTS engine and the word count. And here is the video preview in the UI. I hope the sound will work.
In this tutorial, we will learn fade in images with a placeholder.
So this is for that scene. And you may notice that our pipeline controls the motions of the head pose, the lips, and eyes. In the next scene, it shows the first text paragraph from the tutorial, and the text content refers to an API keyword. And in this case, our system chose to highlight this keyword as a text overlay, and here's the video preview.
When displaying images using the default image widget, you might notice they simply pop onto the screen as they're loaded. This might feel visually jarring to your users.
So the following two text paragraphs refer to the same API keyword. In this case, we just automatically combine the two things and to highlight the same keyword. In cases where the original document, the API names are different, and users can choose to manually merge things in our UI, where our system will automatically select a suitable layout, and from here the text overlay to a side-by-side view. And here is how it works in action.
In this example, use the transparent_image package for a simple transparent placeholder.
So finally, users can choose to add it and switch between different layouts. And these design choices are based on our observations from 40 public videos of different authors and platforms. We observed that in such instructor-led videos, a talking head shot is often placed as a full screen, or a side-by-side view with code snippets, or a picture-in-picture view, such as on an IDE. And similarly, a text title can be placed in a full screen, side-by-side with a speaker, or as an overlay with some animation. And our goal is to really extract the content from the document and suggest such presentations for editing. And now I'm going to go through our automated pipeline. So given the text document, we first parse the content and analyze the text nodes. And our current pipeline parses markdown annotations from an input document. This enables us to identify paragraphs and their types, such as the title, code block, as well as the text elements, like an API reference. And next, we break down a document into scenes and plan a video script. And for text content, we generate a talk script for narrations. And for other elements like code and images, we suggest their visual presentations that will be shown in the video frame. And we merge content that refers to the same concept. And with this refined script, we then decide a graphical layout for each scene. And next, for each scene, we convert the narration sentences to a text-to-speech audio file. And each audio is then used to generate a synthesized talking head video. Our work is based on LipSync 3D, published last year at CVPR. And it is a video-based learning framework for animating personalized 3D talking faces from just audio input. And one advantage is that this framework takes audio input to generate 3D face mesh and synthesize the face mesh with lip motions to the target videos. And this makes it flexible to generate videos of any length given the audio input. Also, LipSync 3D can generate both animated characters, as you see in this talk, as well as the photorealistic subjects that we chose not to disclose in this publication, although we have done internal experiments with permissions from the speakers. And finally, we compose the source documents and talk script and visual highlights all together and render in this web UI for interactive editing. So users can truncate a sentence and playback, etc. And we ran our pipeline through 65 open source programming cookbooks. So a cookbook is a tutorial in shorter length. And please find more details about the results in our paper. And finally, I will briefly go through our evaluation. So we invited 6 professional creators from our organization. They are specialized in developer education, and they're from different, three different public programming platforms. Although they all work for Google, but each team actually has different practices, different styles, and different communities. So our study has 2 parts. The first part was to understand their existing workflow. So it's here's just some high-level findings. So we found that their current practice includes they will always start with a script in Google Doc, and they will create a table of 2 columns. One is the narration, and the other is what they want to show in the video presentation. And in the narration, in the video presentation, they will specify the title, the code, the screenshot, even the animations, and the rough layouts for communication. And they will just copy and paste content from a document or directly from the code editor into the table. And they will edit and highlight and annotate the timing. And they will just iterate and finalize the script before going to recording. So they will first do some dry runs and table read and make sure all the script is as what they expected. And once they move to the recording phase, they will just follow the written dialogue from the script using a teleprompter. And they'll rarely go back to re-record their materials. So the second part of the study is we show our interface given the tutorials, and we asked for their feedback. So first of all, they found the scene breakdown matched their current workflows. So one participant said, "It shows me the source. It helped me understand why it made decisions it made." And the second part is the video previews. So we originally had some assumption like maybe to make things easy, why not we just use the TTS audio and just use some animated video for playback. But actually participants found the lip syncing actually really helpful. So one participant said it will be weird without lip syncing. It makes it also more fun to use the tool. Also, the animated character was pleasing. So the polar bear here, it makes it more like imagining like you're the instructor going to be in the final video view instead of seeing yourself being rendered in the video preview. And this is also something like the lo-fi prototyping that we can refer in the HCI research. So finally, we found that editing was definitely essential. So participants definitely say they want to have a lot of control for the final text and video because the text in the document is mostly for reading, so they may not necessarily be transferred to the video script. So we found some opportunities. Definitely, we want to support more context-aware like rendering. So for example, like some creators will have personal styles, they want to change the tone to make it more fun and more dialogue, and they want to change the visuals. So these are all things that we can definitely improve. And also really to support this kind of end-to-end video production. So with more fine-grained control and really to support the recording phase in the next stage. And we want to support more domains. Also, this work, we focus on programming, but we imagine we can apply to like science, art, and other fields. And with that, yeah, I will conclude my talk here, and I'll be happy to answer questions. Thank you.
I was wondering if you had thought about that. And the next question is like whether like just translated version of the text document, but like augmenting some parts, like highlighting some codes or like adding some examples not in the text document. So yeah.
Yeah, great questions. So the first part, yes, definitely we're trying to really index the video eventually better and better, because now it's almost like every stage is disconnected. So if we can maintain that link, then once you publish a video, we know the exact point of time in the video, then we can really, for YouTube, for example, there is a card that you can click on that and then take you to the exact point of the document. That's something that we want to really look forward. And enhancing that is definitely the next step, really how to highlight things when you speak to the certain keywords and there will be a highlight. I think there is something that definitely we can borrow a prior work for that. Thanks.
Thanks for your serious work, I think, from UI to video to desktop to video. So my question is like, I think all of this work are basically based on very structured input. So have you ever considered like how to handle the document or the text that is not in a well structured?
Yeah, definitely a good question. What about news articles or blog posts, etc.? So apparently we do have some underlying assumptions about that, but I think for machine learning techniques, they're better and better. You can train, you can know the structure and better. Really finding that underlying structure in the previous talk, for example, like cutting to shorter version, and that can all come along. But currently we focus on this because then maintaining that structure helps us to break down the things better. And so it will be more like consistent. Users can know the mapping, almost like if you annotate in this way, then the map output will go in that way. But I think it's a really interesting problem about like generative models and how we can work with a machine.
And I also noticed that from web page to tutorial, like the content actually got more complicated.
Yeah.
So just an interesting question, like have you ever considered, actually on YouTube there are lots of video is about talking about a paper.
Yes.
So have you ever considered like how to handle this kind of like more complicated stuff?
Yeah, like the 2-minute video paper thing. Yeah, definitely. Like the concept is so complicated, and then probably they will only talk about a high-level thing, and you kind of want to look into the details. And how do you find the balance into that? That's a really interesting question. We can talk about offline. Thank you. Yeah.
Hi, thank you for the great talk.
Thank
I was
you.
just wondering, you said you tested on people who are already employed at Google. I was wondering if you would consider in the future testing with like amateur video creators, or maybe some of the types of creators that you base this technology off of.
Yeah, great question. We actually thought like, professional creators, they may already used to that. And then for amateur users, maybe they will find this even more useful. And that's really the next goal, like even run external studies. And even there are like amateur video creators, but really already have a video channel. They already have some personal style and only one-person team. And that maybe make this even faster for them. Yeah.
Thank you.
Thank you.
Do you mind just shifting a little bit to answer the next one? Just
Yeah.
a second. Just keep talking.
Hi, this is Venkatesh Kasturi from University of Washington. Really cool work and great talk. I was wondering, since from what I understand, a lot of the visuals and artifacts are also generated. Is there a scope for, or have you done any experiments with making sure that these videos are accessible in the sense that they have audio descriptions of the visuals or other components? Envisioning a world where people share these videos and not the documentation.
Yeah, I really like the point that because we actually have the text document, everything is already written and can actually be captured to enhance the video. And how we can maintain that structure and even enhance that for better understanding. And that's really really one thing that we want to look for.
Thank you.
Thank you so much. Thanks a lot.
Okay, we're going to try to keep these to around one question per presentation for the next few. Sorry about that, we're just running a little bit behind, but the authors, again, to remind you, will be here after the session as well. But our next talk will be by Jian Liao from University of Calgary, who we briefly heard from at the beginning in the lightning talk. And Jian will be talking about speech-driven approaches to augmenting interactive live presentations.
Okay.
Thank you, Jane, for the introduction, and thank you all for coming to our talk.
And I'm very excited and honored to present my work here, as this is my first UIST conference. So my name is Jian Liao. I'm an undergraduate student from the University of Calgary, supervised by Dr. Ryo Suzuki. Today, I want to talk about Reality Talk, a real-time speech-driven augmented presentation for AR live storytelling. This is a collaboration work with Adobe Research and University of Calgary, and is co-authored with Adnan Karim, Shiraz Jaden, Rubaiyat Habib, and Ryo Suzuki. Okay, so now let's get started. So this talk is about augmented presentation. And you might be wondering, what is augmented presentation? Usually when we try to present something, we use this kind of slides and also this kind of presentation style, which is what I'm doing right now, and I assume it's pretty boring. But however, how can we make such presentation like more fun and more engaging and more attention grabbing? So back to the question. Augmented presentation is a presentation technique that leverages embedded text, visuals, and animations onto the screen while you are presenting to enable a visually engaging, memorable, and expressive storytelling experiences. So this kind of augmented presentation are mostly seen in some YouTube videos with this kind of like embedded text and visuals, which provides a more expressive and memorable presentation experience. However, such augmented presentation are mostly created with post-processing video tools, such as After Effects, which can take a lot of time and effort with video editing and programming. Moreover, such post-processing tools are not suitable for live presentations and interactive experiences because they are not presenting in real time. Now let's take a look at an augmented presentation practice using Reality Talk, which present Reality Talk.
Adnan Karim, and I am a graduate student at the University of Calgary. Today, I want to talk about real.
I need to.
Can you open your sound?
Okay, sorry.
So yeah, go.
Sorry for the mistake. Hi, my name is Adnan Karim, and I am a graduate student at the University of Calgary. Today, I want to talk about real-time augmented presentations. As you can see, when I talk about something, we can augment presentation using an augmented reality interface. We have several features, such as kinetic topography, embedded visuals, embedded icons, and embedded annotation to a physical object. All components are interactive.
So as you can see, while presenting, the system allows the presenter to embed dynamic text, visuals in real time to create such augmented presentation. And the core contribution of this work is by incorporating real-time speech recognition and natural language processing with keyword extraction to create such speech-driven augmented presentation. Now let's take a look at the Reality work. To solve the non-improvisational problem with the current video editing techniques, there are many existing work focusing on the improvisational aspect of the presentation. So compared to traditional video editing techniques, prior works have explored live augmented presentations, such as interactive sketch-driven by Chop Talks, and gesture-driven by interactive body-driven graphics, while speech-based interaction techniques are relatively less explored in this setting. Thus, the goal of this work is to facilitate an interactive storytelling experience by enabling the presenter to prompt, embed, annotate, and manipulate textual and visual elements in real time. Now let's take a look at the example.
Hi everyone, I'd like to introduce this new water bottle. It has so many benefits, including double wall vacuum insulation, this flexible perforated handle for easy use, and it's dishwasher safe. You can bring it with you to so many different activities, including going to the gym, you can bring it to the outdoors, and if you'd like, you can even bring it to the pool.
So as you can see, what the presenter is presenting, this is like an e-commerce example. the presenter can embed many dynamic visuals as well as annotations, a list of textual elements that could be attached to a physical object. Also, in the end, you can embed a QR code for the audience to scan to just buy the product like right away. So to better understand the common interaction techniques used in augmented presentation, we collected a data set of 177 existing augmented presentation videos, and there's an interactive gallery which is available on the website over there. Our initial findings suggest a design space which can be break down to 4 dimensions, namely textual, visual, location, and interaction. So for the textual elements, we noticed that from the existing examples, we found there's so many textual elements that was driven by the speech. For example, a title and keywords that was indicating the title of the presentation, a list of textual elements indicating like the features of products, or maybe labels and annotations that are attached to a physical object, as well as a profile caption that was showing personal information of the presenter, as well as a speech bubbles. And for the second dimension, which is visuals, which is mostly common seen in this kind of augmented presentations, such as static visuals, icons, as well as videos that you can play within the presentation in real time, as well as interactive screen, such as a user interface that allow presenter to embed in real time. We also see many other visualizations such as graph and 3D models. So once you have the textual visual elements, then we need to figure out like where you put these kind of elements within your presentation. So the system allows presenter to embed these elements in the front or in the back, or even on a 3D surface, and even attached to a physical object that will follow the object movements, and it can also be body surrounding. So lastly, we are also very interested in how the presenter interacts with the elements. So first, the presenter can specify the position where the elements pop up by simply just using a pointing gesture, pointing, and then you can get the elements will pop on that position. You can also use a pinching gesture to move the object or drag and drop the object. You can also use both hands to scale an object and maybe also rotate it. And you can also have the follow-through effects which attach to your hand movements, which is essentially motion tracking. And we also see other interaction effects such as triggering and highlighting effects as well. Now let's talk about how we implemented the system by dividing the workflow into 2 phases: the preparation phase and the presentation phase. So during the preparation phase, the system provides an offering user interface to allow the user to register the keywords and associated visuals using a keyword matching approach. Then the user-defined visuals can appear on the screen based on the spoken keywords during the presentation. And during the presentation phase, the system incorporates real-time speech recognition using Web Speech API, keyword extraction using SPACY, gesture recognition using MediaPipe, as well as visual embedding using A-frame, object tracking, and as well as word tracking. Now let's take a look at the summary of the application scenarios. So we discovered that our system could be used for business meetings, online lectures, and e-commerce live stream. So the first example is an online lecture.
Hello class. Today we're going to discuss white blood cells and killer T cells. In particular, we'll talk about the HIV virus and how it attacks the blood cells and hides from the T cells.
So the presenter is a high school biology teacher trying to demonstrate how HIV virus invades our immune system. The presenter can use this kind of animation to demonstrate how HIV virus attack the blood cells, and showcasing a immune system diagram, as well as a video that's showcasing how this works. And the second application is for a business meeting.
My name is Jane Doe, and today I'm going to present a sales report for the last year. We have 2 main products, the first being the Canon camera, and the second being the Sony. As you can see in this chart.
So in this example, the presenter is a business analyst trying to present the sales report of the cameras, and then the presenter can embed the two product photos within the presentation, as well as a sales chart showcasing the sales target of the next month. And the last example is the example that we've seen before.
Hi everyone, I'd like to introduce this new water bottle. It has so many benefits, including double wall vacuum insulation, this flexible perforated handle for easy use, and it's dishwasher.
So in this example, the presenter is like a social influencer trying to sell the products using social commerce, and then the presenter can make the selling experience to the audience much more engaging by leveraging our system, as well as showcasing a QR code for the audience to scan right away and get the product. We also conducted a user study with 15 participants, and we evaluated our system from a presenter perspective to demonstrate the features and effectiveness of our system. And all participants are required to do a 5-minute presentation, and the feedbacks are overall positive. I'm not going into details. You can refer to the paper for the questions. And lastly, we'll talk about the discussion and future work. So for our future work, because the users still have to prepare in preparation, because so we are interested in seeking for a semi-automated suggestions using existing database such as Google image search. The second is a customizability of the presentation. So usually this is a very improvisational techniques. So a certain degree of customizability would be we produce a more sophisticated presentation. Also, we're interested in deployment in the wild by empowering the YouTubers using our system to help if they can increase their engagement with their audience. And we're also interested in how we can integrate reality talk into the HMDs or spatial AR. And lastly, we are interested in expanding our applications to augmented conversation as well as discussion. Okay, this concludes our talk. Thank you, and I'm happy to take any questions. Thank you.
Fantastic model and wonderful work. I'm Jenny from University of Toronto, and I'm wondering, like, if you think about, like, it seems that the current approach relies more on sort of reaction to nouns, like keywords extracted from, like, like maybe is my understanding correct? Is it focusing more on nouns, or it actually can sort of operate on more complex content?
Yeah, I see. Yeah. So right now we are only detecting nouns, which is we think is more related to your presentation. Like if we, mostly nouns or entities that we can be associated with visuals. So we are not detecting like verbs or any other words. Yeah.
Yeah, it seems there's a huge potential to like maybe like expanding on the. Yeah, I was wondering if we can elaborate a bit on like other kinds of linguistic concepts, like.
Yeah, for sure. Yeah, thank you for suggestion. Yeah. Thank you.
Yeah, let's thank our speaker for the talk. Okay, for our final talk of the session, we'll have another presentation sort of in this like live augmented presentation domain. Brian Hall from University of Michigan will present their work that enables communicating data through sort of mid-air gestures. And also let's congratulate the authors on their honorable mention.
Oh, thank you so much. Thank you. Just plug it into the end thing last time.
I actually use this one, but
Oh,
I don't know
yes,
if that
that's
matters.
everyone's favorite part is the plugging in.
Worked fine last time I did this, right?
Yeah. I just had to switch this side.
Yeah, I just have to make sure.
And that's
This one
Yep,
is
that's
HDMI.
HDMI.
Okay,
That's great. And then I just have to move. Oh wow.
Okay.
Or let's full screen. Thank you very much. Now, I just want to start by acknowledging that this project was developed remotely, working as an intern at Tableau Research, and my great mentor, Matt Bremer, who's here as well at the conference. And this project is actually about presenting remotely, and yet now I'm presenting it to you here in person, which is ironic, but here we are. Now, I would like to start with a motivating example. The fact is, presentations around data, with data, can be very compelling. And as an example of this, I'd like to show you a short clip from the late public health expert, Dr. Hans Rosling. Now, you would be hearing something, but we're not currently. Worked earlier.
No, it worked earlier.
I know, right?
Sad.
Oh, well. It worked before. Oh, you know what? What if this occasionally, let's try.
Another option is like when you plug in this cable, it does work, but it doesn't get recorded through.
Yeah, I could just play it on the audio, or I mean, I could play it on.
So like this one messes with the recording a little bit, but it does work.
I'm just going to try something unusual. Just a moment of technical difficulty as we try a workaround here, so you get to hear it, because that is part of the experience. Oh, that one was, sorry.
It's I wasn't sure if someone had a suggestion.
Oh, no, it was a gift, but that was a sound one. Go. Well, I don't know anything about reality.
Maybe for now.
Can we do those workarounds?
Because we're also good at something.
Oh, well, that's been, yeah, that's delightful. It worked so nicely before, darn it. Email cannot be loaded.
I think the video is not loaded, and the thing is, it doesn't have audio as a GIF, so that's
Oh,
why.
there's a GIF second. There's an audio first.
Yeah, but I think that the audio video was never loaded. It
Oh.
says video
I was
wasn't
always
loaded.
playing the GIF.
Let's try that.
You see? Yeah, okay, perfect.
Oh, that's okay. That may have actually been wrong. Let's try one more time.
Are the sound settings still correct? Because we can fidget it with a bunch of things.
Yeah, they did. Let's see.
Plug in the cable or not?
It usually works through the other
Yeah,
one,
yeah.
and that was the preferred method.
Let's try this, maybe?
It is.
Digits. Oh, wait.
Maybe
this.
it's changing.
Okay.
Test? I don't know what that means.
Yeah, that's the surround. That's unfortunate.
Go back. Yeah, maybe just try this one.
Yeah, let's try that one.
Is this even plugged in?
Which one did you open? Sorry, this one. Yeah, that's right. And it doesn't see it at all.
Just
But why?
give it a
worked
shot.
perfectly.
Oh, yeah. Let's totally get
It's
those
so
about.
smooth.
Oh, I can hear something.
Where is that?
Oh, okay. I think
Yeah, I can hear something, but I don't know where.
I think that works.
Okay, let's
Okay,
just
it's a little
go with
quiet,
it.
but you know what? We're just going to roll with it.
Because the settings. Okay.
Oh, sorry.
Okay.
I think we can roll with it. Oh. Okay, so when presentations occur, they can be compelling. So we're going to see what that looks like right now. Now, why do we consider this so inspiring? Well, for one, this presentation allows the personality and passion of Hans Rosling to show through the data. And it does so in a way that does not obscure the very facts that he was trying to communicate. Now let's contrast this with the reality of remote meetings, where we spend so much of our working lives. In this remote meeting, the primary view is a shared screen, usually static slides, or in this case, a business intelligence notebook like you see here. The presenter is a head in a box off to the side. They might be showing a mouse cursor or a yellow laser highlighter to help out. But it's not a secret that many people have trouble paying attention in meetings like this, and presenter and attendees both often find them tiresome. It's hard to direct attention across visual elements with just a pointer, and mouse movement to control the interface can be distracting. Even in an interactive visualization tool, it can be hard to respond to audience questions and discussion effectively, which is often the very purpose of having these meetings in the first place. Now, pushed by our own frustration with the status quo of remote presentations, we wanted to not just bring back some of the affordances of standing near a screen like here, but we wanted to go a bit further. However, the example you're seeing was a recorded BBC special produced over a decade ago, and all of the effects are the results of post-production and clever acting. It looks like Hans can see the data and is staring at them, but he had to learn that. It was acting. But now, is it possible to bring experiences like this to live remote meetings using only standard computers, basic webcams, and publicly available computer vision software? Could this enable meetings that are more engaging and which would more often result in the kinds of discussion that are so powerful and fulfilling yet so rare to experience in practice? So today I'll be walking you through our touchless approach to presenting data to remote audiences. The video examples I'm about to show you were made within the presentation environment, and that incorporates our approach. And the presentation it is about the changing costs of higher education. Now, these are examples, these interactions, of deictic highlighting and brushing using the hands. Now, the hand can be held in any natural feeling orientation, such as an open hand or a single finger, to draw attention to specific visual elements. Either hand can be used for single-handed interactions like these, or the system can switch to preferring the dominant hand, allowing the off hand to be used for other gestures that are unaugmented if the presenter would prefer. And let's look at some more interactions. Now, for these interactions, one can use both hands in concert to manipulate the visualizations, In the one example, I'm using a crimping gesture to provide a new overlay, a total for the stacked area chart. In the other example, I can pick up data points on opposite sides of the screen to compare them visually. And ultimately, this could be done for any chart element where the feature is enabled, which allows the presenter to respond dynamically to audience questions. And we'll look at one last set of interactions. Now, the key concept we're illustrating here is what we call rhetorical flourish. Now, in the snap example at the end of the video, and that's shown on the right of the screen, technically I only needed to press 2 of my fingers together into a pinch to reveal that data. However, the system did not require the snap sound or the motion to trigger it. Actions like this can nonetheless enrich a presentation by focusing attention and building anticipation of what's about to happen. As a presenter, it's also pretty fun to perform. Now, but more broadly, we believe that this actually is an essential design consideration, and it can allow for a system to suit different presenter styles or allow a presenter to adjust their delivery for different audiences and topics. Now, in terms of how we built this system, I'll keep this brief. We built it in JavaScript. Again, we want to reiterate, it only uses a basic computer and a basic webcam. There's no additional instrumentation. The Google Media Pipe is used for continuous hand tracking. And also, the system is a what you see is what I see design, which is to say that there's no alternate presenter view. We found that it was most helpful, what was most helpful for the presenter very often ended up being helpful for the audience to see as well. So there's a shared common view. Now, to push beyond our initial design intuitions, we did conduct 2 user studies with a total of 12 presenters and 17 remote viewers. And this is just a quick peek from the perspective of one of our participants in the presenter study. And we did try different room layouts and different attempts, but actually you can come and try out the experience for yourself. Tonight at the demo session, we'll have an interactive experience. Fingers crossed. We hope to see you there. But one thing we did wonder about was how would people use this system who may never have seen it, who've never tried something like this. And this participant, I think was particularly interesting. There's a quote here, but also if you just notice the way she uses her hands, it almost has a kind of very smooth, a fluid, smooth, almost musical sense to it. And we didn't teach her that. That was just how she used the system by default. But not all participants use these things the same way. So for instance, the participant on the left here, if you notice, he's pointing at the screen and straight out at the viewer, almost like he's trying to reach something that's out of his reach. That's very tiring to do. We didn't tell him to do it. That's just what he thought he should do. But it's much more comfortable and much less tiring if you're working with your hands near your body the way you normally would just speak naturally. Now, we also examined from the audience perspective, where we gave part of our presentation in our environment and part in a screen-shared business intelligence workbook like you see here. And the big takeaway I did want to share from this portion is that we did find that there's this potential to engage and also distract with the same thing. These run together, and you have to be careful about them. And this quote was particularly summed it up is that participants said, "I'm actually listening more. I'm paying attention more because I'm more engaged by your physical body. I like it better now that it's clean and doesn't have all those numbers I was looking at before. In this version, I'm able to just listen to your voice and focus to the story. My heart is more patient with you." And to bring to summation here, to reflect on our approach and findings here. Do note that there is a tension between gestural interfaces. So work that typically focuses on how do you use gestures and hands to control an interface, as opposed to part of the namesake of the paper, chironomia, which comes from an ancient Roman statesman, Cicero, that described chironomia, defined it as manual rhetoric, or the art of using the hands to make an argument or part of a discussion. And these can pull in opposite directions. And actually pushing towards the future, that's part of a concern. So one is simply recognizing operational gestures. These are like computer vision, technical tasks. Google MediaPipe is incredible. There are other tools like this, but that work is not done. There's especially challenges using it like this. Detecting a finger that's out of focus or when hands cross can confuse these systems, and there's still work to be done there. Also, a matter of assigning gestures based on frequency, how often people may use them, but also salience. What gestures are impactful that tell a story this is going to be socially negotiated. It's going to be cultured. It's going to be defined by how people use them. And this is the social question of what happens when people are using them. But we do have to pay attention to it and consider it. And then finally, to do no harm. To quote Shakespeare, striving to better, oft we mar that which is well. And if our purpose is to put people back into a presentation so you can see them, they can use their body, it can be very easy to try to augment it and make it worse and make it harder so they feel like they can't use their hands at all because it's going to mess up the system. And that would be a very unfortunate outcome and that we had to be careful with, and it requires restraint and consideration. And to bring this to summation and to close, well, this is the end of this presentation. I hope it's only the beginning of our chance to converse. We have our demo tonight, and we'll be at the conference. And finally, I'll be looking for a job next year, so on the job market. But with that said, thank you very much, and I hope to open up to whatever we need to do next. Thank you very much.
I was just wondering, is there maybe some feature capability for multiple people to interact with the same data? So like if a participant had a question about a specific chart, they can maybe like highlight it with a gesture or move it around or somehow interact with the presenter and the data.
Yeah, no, that's a great question. And actually, that's one thing we sort of wondered about, right, is that especially for actually getting to that conversation and talking about it, like being able to like hand off data, technically speaking, because of the way this is it's pulling in a video feed into the recognizer. You could, in theory, change how that works, right? It could switch off video feeds or use an alternate one. There's no technical reason that it can't be done. We didn't implement it and haven't done that yet. But this kind of collaborative handoff, either multi-person at the same time or back and forth, I think that's a really interesting area going forward. Absolutely.
Thank you.
Certainly.
Hi, thanks. That talk was really rad. This is really interesting. I know this is mostly focused on presenting data, and in this case, it was focused on certain types of charts. Do you think this extends beyond specific like presenting charts? Could it be other types of content, and does that utility extend beyond that?
Yeah, absolutely. So great question. And that's so funny. When I was closing my internship, my internal presentation, I gave it in this tool. I just moved all of my slides. Instead of in a slide presentation, I gave it in this. And it included elements that aren't strictly charts and visualization, so pictures and other things like it. And that was really nice to do. I would have done it here if I had any idea what the setup could be, and it might not work. But also like looking at the other talks, things like code. Could it be code? Could it be pictures? Could it be other ways of presenting? I think that's really interesting because we focused on data and visualizations really to ground what we were doing to tell a certain kind of story and to help us figure out what the heck to do and to bind it practically. But I think that's a wonderful area that it really could be. I think it could be extended to that. I don't know where it ends, and I think that's going to be a great question for people who want to work on it is, when is this good and when is it bad? And what other virtual objects can we do it with, and does it help, and how? How would you gesture with it? So, yeah, the mind wanders, but I think that would be great to see, yeah.
Cool, thank you.
Certainly. All right, get out of here.
Yeah, let's thank all the speakers again. And thank you all for sort of staying and listening for the end. And just a reminder again that the speakers will be here, so come up and ask them questions, especially since we had to rush some of the questions. Thank you.
Okay. Hello, everyone. We'll go and get started. Welcome to session 3A. This is Novel Interactions. My name is Eric Whitmire. I'll be your session chair. I'm a researcher from Reality Labs Research at Meta. I'm really excited for this session. This is going to be a really fun one. We have about 90 minutes together. We're going to be looking at all kinds of new interactions and new systems that enable interactions. In this session, we've got lasers, we've got slime mold, we've got walls that move. It's going to be a fun one. There's something for everyone. And I'd encourage everyone to give the fabulous presenters your full attention. We're going to have, I think, something inspiring for everyone here. Before we get started, we have a couple of lightning talks, so let's get it rolling.
Hello, my name is Frank Liu. I'm a fifth-year PhD student in computer engineering at Arizona State University, and I build haptic devices for science education. My goal is to bring the physical science lab to students' fingertips, to democratize mixed reality experiences regardless of situation or circumstance. I've built novel haptic interfaces that simulate the sensation of virtual fluids. They can be integrated into virtual science labs and other training scenarios. I've built education modules which use symbolic overlay to enhance science instruction and support existing curriculum. I want to change the way people approach and experience education in the metaverse. Come say hi to me at UIST.
Hi, my name is Gabriela. I am happy to attend UIST. I'm interested in HCI haptics wearables, IoT and computer vision for human augmentation and well-being. I am a bachelor student in electronic engineering in Peru. My research experience includes the Interactive Organisms Lab advised by Katia Vega, the Empathic Computing Lab in the University of Auckland, and right now in the Max Planck Institute for Informatics at the Sensorimotor Interaction Group. At the EO Lab, I work in the GoFlex project, which is a wearable device to aid in canine flexibility activities. It uses 2 IMU sensors to calculate the joint angle in real time and then provide feedback to the user. And right now in the Sensorimotor Interaction Group, I am exploring new ways in which the compliance solution can help us build new haptic augmented reality devices. I am a first UIST attendee and feel free to reach me out at any time and follow me on social media as well. Bye.
All right, I see Frank over here somewhere. If you want to wave. Gabrielle, if you're here, do you want to wave? Awesome. I hear both of them are looking for internships for next year, so you know who to talk to. If our first speaker, you want to go ahead and set up? Our first paper is called Flexel, a modular floor interface for room-scale tactile sensing. Taka will be the presenter, Taka Yoshida.
Yep.
One of the co-authors, Naomi Okazaki, Ken Takaki, Masaharu Hirose, Dr. Shinro Kitagawa, and Dr. Masahiko Inami. And I believe Taka is also on the job market, so keep that in mind. Take it away.
Hi. Okay, thanks for the, oh, may I take, okay, masks. Okay, thanks for the, the warm introduction to me. I'm Taka from the University of Tokyo. So today, I'm so happy to present our Flexel interface, a modular floor interface for room-scale tactile sensing. So first of all, here is a quick question to you. This image captures an aspect of my body activity. Can you tell what this image represents about? So here's the answer. I'm sitting on the chair, wiggling my body, and standing up again. And can you see some correlation between the motion, my motion, and the patterns in the floor images? The most important insight today I'd love to provide to you is a floor image tells the user activities a lot. On the left figure, the footprint on the chair appears on the floor. In the middle figure, the floor image captures the user leaning on the tables. Okay, let me briefly tell the motivation for why we work on making such a new floor interfaces. So here's a survey of human sensing. They summarize the many physical channels to access human activity properties, like the camera can capture human shapes and motions, wearables capture heartbeat and sound, and so on. So we focus on the floor sensing. Floor sensing has its unique feature of accessing the weight and vibration channel of the human activity. So this kind of floor-based sensing approach gets its traction more and more in our HCI community. Here is a survey paper that recommends us to use the floor surface more as ambient interfaces. They summarized and listed 10 advantageous features of its approach. And we particularly focus on the ubiquity and unintrusiveness that is so attractive to us. Then, how have the researchers, in the past researchers, designed the floor interface in the past? In the prior works, we observed 3 main form factors of the floor interface. The first type is a surface type floor interface, which usually appears as a carpet type interface. The second type is a structure type, which is hidden in the architecture bodies. The final type is a spatial type, which modifies the whole room space beneath the floor and achieves rich spatial experiences. From sensing perspectives, there's a wide range of spectrum in sensing resolutions. Finer pressure sensors have 1 centimeter sensor pitch. In contrast, a force plate on the right for an athlete, sports athlete, has a 50 centimeter sensor pitch. So however, there's no guideline how we should choose a specific sensor resolution to achieve a specific task you wanna achieve. So in this presentation, the key question we have attempted to solve is how can we design a new floor interface for only a purpose? Imagine there's a lot of floor sensing applications like retail analysis, fall detection, sports analysis, and so on. Here we provide a generalizable design guideline for new floor interfaces. So designing a floor interface has 2 major aspects you need to consider about. Since our floor is a component in architecture, so we need to investigate the preferable design from an architecture point of view. On the other hand, at the same time, the floor interface is a human sensing platform, so we need to figure out the required sensor density that achieves the necessary performance with minimum cost. To answer these questions, for the research question number 1, we visited the construction site with architects. We observed the 2 major archetypes of floor materials, that is sheet floor and structure floor. Notably, both of the materials are modularized for ease of constructions. Then let's think about how we utilize that floor modules as a sensing platform. The sheet floor can be utilized as a pressure sensor sheet with cell-wise intensity measurement. On the other hand, this is important. The structure floor usually has 4 rigid legs at the corners. So when we put sensors on it, a cell in the structure type floor can capture the cell-wise intensity and the floor center of load at the same time. We will investigate how the difference in the form factors affects the performance and the required sensor resolutions. Here we care about the required sensor resolution to capture specific target, like foot centers or foot orientation. We focus on the foot properties like as a primary sensing target because it has a continuous contact with the floor surface. So making the cell size larger, the captured image becomes more ambiguous, right? So which means they lose information to reconstruct it. We figured out the threshold by computational simulation. So here's the result. How the cell size contributes to the foot center and foot orientation estimation. For the left figure, for the foot center detection, the structure floor always correctly reconstructs the foot center. The sheet floor has a 1 centimeter estimation error when the cell size reaches to the 16 centimeter. For the right figure, the foot orientation detection. The sheet floor works if the cell size is less than 8 centimeter, and the structure floor works if the cell size is less than the 18 centimeter. So here we summarize a generalizable design guideline which applicable to your floor interface. So from an architecture perspective, the interface is preferable to be modularized. Also, the requirement from the architecture context, like surface replacement, you should determine the type of the base material. From the sensing point of view, you can follow the cell size table to find the appropriate sensor design to your interface. So we also follow this guideline to fabricate our own proof of concept modular floor interface. So in the right figure, I show the final CAD design of our floor interface. From the architectural perspective, we decided to use a 50 centimeter modules to fit the convention of the construction. Also, we use a cell size of the 16.7 centimeter to enable foot orientation detection. So our floor interface is prototyped based on a modularized raised floor. So it is easy to install to any kind of ground surface, just tiling the modules on the ground, and it immediately works as an interface. Also, since we enable the surface replacement, it accepts the various surface materials from the thin carpet to thick 1 centimeter wooden boards to artificial rounds. So it fits adaptively for room context. So as a total, we implemented a number of floor modules like this. So here, so please watch out our engineering efforts. In addition to the hardware, we also built floor softwares. The hardware modules are connected to the floor PC, and the software aggregates all the input data into the single unified image format, which we call the floor image. The floor image can be used as a fundamental source for the
for interaction with information, such as 3D modeling, physical computing, tangible programming, gaming, and context construction. However, computers become too expensive and cumbersome to maintain when these systems are deployed at scale. To support deployment at scale, passive solutions were proposed. For example, this UHF RFID system, RFI bricks, supports sturdy physical construction of building blocks to be identified. However, the system requires infrastructure such as a UHF reader, and they cannot support concurrent events, which frequently happens in assembling smaller units or in multi-user interactions. Also, to detect the stack events, existing systems use electromechanical connections to force the physical alignment in stacking, but that also impedes further tangible interaction. So we ask further, what if these building block systems can support frictionless interaction? What if they can support more fluent and versatile tangible interaction if needed? That's why we aim to support both concurrent construction and frictionless tangible interaction in this work, NFC Stack. Now, let me explain how to achieve these goals. In this project, we use near-field communication, NFC. NFC is a low-cost and lightweight system that has been widely applied for applications, including payments, door access, and toys. An NFC system supports wireless communication between a passive tag and its reader. The reader transfers energy to a tag and uses the modulated signal to identify the tag. The communication is reliable. However, the reading range is often shorter than 5 centimeters. The reader antenna must be extended to identify the block stacking. We explored 2 antenna extension methods. The first method is called transmission line extension. We extend the coil's location from the reader by using a pair of parallel transmission lines. This method has a small footprint, which is useful for miniaturization. However, these blocks must be strictly aligned, since they depend on mechanical connectors. Therefore, we need another extension method. It's called multi-hop extension, which is based on wireless induction. We use a relay circuit, which is a pair of coils, to pass the signal from end to end. A big advantage is that these coils do not need to be strictly aligned. Physical contacts are also not necessary. However, to ease the alignment, the coil requires a larger footprint and is much bigger than the connectors in the first method. We designed 4 types of graspable building blocks based on the 2 extension methods. The first type is the station, which is the heart and brain of our system. A station supports concurrent stacking with a multiplexed readout circuit. By quickly scanning 12 channels, the station identifies the building block stacking through magnetic connections in different channels. The second type is the brick. Based on the transmission line extension method, each brick extends all the available reader antennas to its top, so every brick in the stack can be identified. The third type is the adapter. An adapter turns the top of a stack into several portals, each acting as an NFC reader. Frictionless tangible interactions can be performed on the top of the adapter. For instance, with an NFC tag attached to the corner of this knob, the station knows the knob's orientation. The fourth type is the box. Based on the multi-hop extension method, each box extends a set of reader antennas to its top without any connectors, so frictionless interactions can be achieved. Also, boxes can be detected when they are not perfectly aligned.
The top of each box still can be used as NFC reader portals. Last but not least, magnetic connectors maintain the alignment of a sturdy construction, even when the stack is moved. In the paper, we described how we optimized the antenna design with a vector network analyzer. Please check our paper for the details. The results of our study show that a station can detect a full stack of 12-layer stacking with bricks. A station can also detect a 12-layer combination of a full stack of 7 bricks, 1 adapter, and 4 boxes, even when each box is stacked on another one with a 6 mm offset. Please check the details in our paper. Now, let's give you some examples to show how these building blocks can be used in applications. For this word puzzle, one user stacks a sequence of bricks with an adapter to set the puzzle. Then, another user can try answering it by interchanging boxes easily, which is impossible with the bricks. By the way, when they are not sure, they can request a hint with an NFC token. With multiple synchronized stations in this music sequencer application, user can construct music sequences with bricks, set the sequences with adapters, and try out the instruments on each track with boxes to make a rich and dynamic performance. In our study, we also investigated the minimum distance between stations and bricks, which was 5 millimeters. Such a separation can be achieved by wrapping the building blocks with a decorative shell. With such a minimum distance maintained between stations and bricks, 2.5 dimension stacking of identifiable bricks can be resolved. Furthermore, with additional pairs of tags and coils on each station sides, the station's relative positions can also be dynamically resolved. Last one, in a tangible programming application, with NFC stack, the user is able to stack the whole line of code composed of multiple bricks and get the functions and parameters resolved accordingly. By the way, in our recent efforts, we also managed to achieve the same functionality with the boxes that supports a more fluent experience of trials and errors. These examples show that NFC stack provides a new means for detecting identifiable building blocks. What makes NFC stack a simple and affordable solution is that most components are battery-free and built from commodity off-the-shelf materials, making the system easy to deploy at scale. Future developers can also enrich the visual experiences by integrating NFC stack into augmented reality, or create rich haptic embodiments using actuators or shape-changing interfaces. The fabrication and durability can be further improved by leveraging pre-assembled printed circuit boards. Making the system waterproof and dustproof is also possible for boxes in a station when there are no connectors on their surfaces. We would like to invite you to read the details of the discussion, check our demo in this evening, and have a chat with us if you are interested in using the NFC stack in your next project. In summary, we have presented NFC stack, which is an identifiable physical building blocks that supports concurrent construction and frictionless interaction. NFC stack is part of the Rich ID interactivity project. We invite you to check other related work through the website here. Thank you for your attention. I'm happy to take further questions.
Thank you for the talk. So many fun examples in there.
Thank
Any
you.
questions?
Hi, thanks for your talk. I'm Koya from the University of Tokyo. And in the history of human-computer interaction, we've seen a lot of types of building definition of this word again?
Oh, yes. So the first contribution is that all our building blocks are all passive. So it's really easy to maintain. And also comparing to other passive building blocks, we support two kinds of interaction. So the first one is the concurrent construction. So which is that we can stack multiple bricks at the same time. It's not supposed in the previous work, like previous passive building block work.
If you want to make the blocks passive, for example, we can use the MagSafe. So what do you mean by the passive building blocks?
Like there are no microcontrollers and battery inside the blocks. Yes.
Any other questions? If not, then while our next speaker is setting up, I'll ask one. An interesting part of this is the use of NFC. It may be related to the last question. Can you talk about what unique aspects that NFC is enabling here? Why NFC and not something else?
Oh yes, so why we use NFC is that we want to make everything graspable. So including the stations, like for the previous work, they use UHF RFID, and UHF RFID readers are really big, so they are not graspable. So with this graspable design, we can bring all these, including the stations with us to everywhere we want. And also with NFC, we can support the wireless connection, so that these building blocks do not need the connectors. So we can support waterproof or dustproof.
All right, thank you so much.
Thank you.
Next speaker one more time. Our next presenter is Zhongyi Zhao, co-author with Toji Yutani. The paper is called Gesture-Aware Interactive Machine Teaching with In Situ Object Annotation. And Zhongyi is graduating next year and looking for jobs, either academic or industry. So if you are looking for someone like Zhongyi, you know where to find them.
Thank you, Eric, for the introduction. And today, I will be presenting our work on gesture-aware interactive machine teaching with in-situ object annotation. My name is Zhongyi Zhou from Tokyo, and this work is done by me and my advisor, Koji Yutani. At the very beginning, I would like to introduce what is interactive machine teaching. And suppose that we have, I guess most of us can kind of differentiate what is a lemon versus a banana. That's kind of an example about what human knowledge we can have like in this society. And IMT research typically are interested in this following question. That is how an interactive system can support human to teach a machine as intuitively as how we teach humans. So here I will give an example on how existing vision-based IMT system will solve these kind of problems. The key idea here is teach a machine by demonstration. So here is an example. For example, if you want to teach a classifier, what you need to do is just do some object annotation in front of a web camera. And after a while, when you finish the demonstration process, the system will automate all the machine learning process for you. And after the training process, the model will be ready. And you can evaluate the model you have already trained very easily. So as you can see in this video, this kind of IMT system typically are quite helpful for typically non-machine learning experts so that they can quickly build their customized MI model for their own use. There also exist several key challenges in this field. That is like the first one, a model created through such kind of simplified teaching process may misinterpret a target object by highlighting unrelated features. As you can see in this video, although the model is like predicting pen correctly, it is actually sometimes highlighting some unrelated features at background. The main cause of this is that when you are doing demonstrations, the web camera is not only capturing the object you hold or like the target object you want to show, but also other unrelated backgrounds. And this will cause some kind of like confusion, confusing definition when you in your teaching process. One naive solution for this is just make annotation so that you can tell the computer that this is the object I want to teach by process the fine-grained annotation. And this will lead to the second challenge, that is the annotation itself causes a lot of workload. And as you can see in this video, that usually it is almost impossible for us to ask the user to annotate each image you have already teach. For example, you have like hundreds, thousands of images in the teaching set. And note that as we mentioned before, IMT systems are typically designed for non-experts, and non-experts typically do not would like to do such kind of task. A summary of challenge in this field is that on one hand, if the user does not annotate the data, the created model will not be that reliable. And on the other hand, if the user annotates the data, the annotation process causes a lot of high workload. So how can we solve it? So please look at me, not the slide here. So this is usually how you do object annotation, right? I guess most of you, when you are looking at me doing the object annotation, you can naturally pay attention to the object that is held by my hand. So that's the key intuition of our solution. So basically, we want to leverage users' tactile gesture naturally performed during the teaching process to achieve the thing we call in situ annotation, which means we want to annotate the object within the image capturing process so that users do not need to do any post-haul annotation. And that's the key of this project. So let me just show you what we have already built. We built a system called Look Here. And this video just shows what we already built in the teaching interface. It's quite similar to the existing work, except there's a key feature on the left side of the interface that we call object highlights. And through this feature, Look Here can achieve the goal that integrate the object annotation process into the teaching process. And such kind of object highlight function can run in 25 FPS. And every time user is clicking on the camera icon on the bottom left corner, and the system will capture a pair of image and label, but also segmentation mask so that user do not need to do any annotation in the post-haul manner. One key technical challenge here is how we achieve this. We consider the targets and tasks we want to do is the object agnostic segmentation task. So that means we want to segment an object without constraining what object it is. And that's quite different from a lot of work in AI community. For example, you want to segment where's Zhongyi, where's Eric, where's the chair, where's the desk, where's like this bottle of water. You usually have a per-defined pool of what category of object you want to segment. And this kind of assumption doesn't work in this system. So we create a new algorithm, and that's the high-level workflow of our algorithm design. That is, given an input RGB image, we first predict an hand segmentation mask, and then we attach this hand segmentation mask to the original RGB image, and then put this augment, so-called augment image into the UNet, and ask the UNet to predict what kind of object user specify through the tactile gesture. So the key intuition of our algorithm design here is that we believe the hand segmentation mask provide important cues on what object users want to specify in their demonstration. To train our algorithm, we also collect data sets, what we call HUDIX. HUDIX is a human tactile gesture data set which consists of around 2K images from 170 people. And we mainly cover 4 kinds of tactile gesture users naturally perform, including exhibiting, pointing, presenting, and touching. Here is just a brief visual result on how our object highlights perform. I just captured some random stuff I have in my lab, and as you can see that the result is relatively good. Sometimes there's some error, but think about it. You don't need to do any post-haul annotation process. everything will be done by the system, so the accuracy is really good. We also conduct a user study to understand the benefits of look here versus 3 baseline IMT system design. The first one is what we call naive IMT. So that's the basic workflow I've already introduced, that is there's no in-situ annotation inside. And also the other 2 baseline kind of design, that is you first teach the system and then you do post-haul annotation. There are 2 kind of popular post-haul annotation tool. One is the basic one, the widely used one, that is the contour-based labeling tool, and that is widely used in computer vision community. And also and the other one is the click-based labeling tool, and that is kind of the representing for interactive labeling tool. In the study, we mainly report 3 kind of metrics. The first one is the model accuracy, including classification and segmentation and accuracy. And the second one is the time consumption. And third one is the NASA TOX. And NASA TOX is kind of like a questionnaire that will report users' perceived workload throughout a task. I won't go very detailed into our quantitative analysis. We have a lot of statics analysis inside. I encourage you to check detail in our paper. But the main takeaway in our quantitative result here is that we already demonstrate that log here is efficient by showing that the model created by log here has a high accuracy while the user do not need to, while the whole teaching process is like low workload. We also collect some qualitative feedback throughout our user study. For example, when participants comment that a group process usually shouldn't contain the annotation process because it's the most time-consuming process, as you can imagine, and it requires a lot of effort. On the contrary, the 2, like naive IMT and log here conditions, are very comfortable to use because there's only 1 step. Also, another participants comment that log here is simple to use, and it also has visualization, so that it can let user keep well informed whether the object is recognized by the computer. To discuss my work, so the main idea of this work is that we leverage human static gesture people naturally perform during the teaching process to achieve in-situ annotations. So in the future, we would like to encourage future researchers to investigate other human interactions during the teaching process or during the communication process. I guess we are like talented with a lot of interaction, but we cannot find it yet. And we believe by leveraging such kind of new human interaction beyond tactile gesture can also achieve in-situ annotation for future IMT system design. To conclude this work, we built Log Here. Log Here is an IMT system that allows users to annotate objects in real time during the teaching process by exploiting users' tactile gestures. Thank you very much.
Thank you, Johnny. Great to see real-time feedback in systems like that. Great job.
Thank you.
Great talk. This is Chen from Cornell. Can you talk a little bit more about like what data set you value are true on? Because the issue with this kind of APT system was actually taking background to cause a lot of issue on segmentations. So what kind of data set you actually applied on, and how your system can generate like different kind of backgrounds and contexts? Do you try that or share more information on the data set to test down?
So the question is like, is there any more information about the data set? I think that's the only thing I've covered in this presentation, but I've already uploaded all the data set file into this project homepage. If you're interested, everything is there. So basically the whole data collection process that we collect data from the Amazon MTurk so that different people can do different kind of object. We ask them to manipulate with different objects without any construction, and that's it. So we can collect a lot of objects of like people can naturally interact with. Well, of course, it cannot cover all the objects people kind of use. And also we ask them typically to perform these 4 kind of dexterous gestures in their kind of collection process.
Thank you.
Thanks for the great presentation. I'm Sungjae from POSTECH. So you said you are using the hand segmentation technique. So I was just curious whether there are specific human groups or some objects making hand segmentation hard.
Oh, yeah, that's a great question. Well, basically, the question is there any typical scenario that make the hand segmentation hard? Is that correct? Okay, I think our main idea is based on computer vision algorithm, and then one typical limitation of computer vision algorithm is that, for example, for example, camera view is like this, and you can only see part of my hand, and the occlusion process is, occlusion issue is usually the limitation of computer vision algorithm. If you just there's only part of the thing that's revealed. And also I find that very interesting things, that is when you use your foot, appears in your camera view, it also considered as a kind of hand, which makes sense. So that's a very fun, interesting kind of, I don't know whether it's an insight, just an interesting finding. Probably computer vision guys need to fix this. And this is foot, this is hand. Yeah.
Hi, Tony. Thank you for the presentation, and it is very impressive to see the real-time feedback. And my question is, since the data collected will affect the accuracy of the trained result, have you think of adding instructions during the data collection process to make sure that we have data from different perspectives and with different group gestures?
Yeah, that's a really great question, because I've always think about this, but it's really hard to guide user how to diversify their data. So what we can do currently is that in the mTurk interface, we show them what kind of diverse way they can do, and also highlight you definitely need to diversify your data. And also we will give you a bonus if you really diversify your data. But we pay them $2 per person. I don't quite remember. So if you really diversify your data, we give you twice, double the price. That's the only thing we can do. We cannot really give them a specific guideline. You should do this and you should do that, and that's really not the diversification. It's we really want to leverage different people's creation. I guess, well, it's not I guess, that's really different if you check the data set. Different people just have very creative ways with different backgrounds. Yeah, it's pretty cool if you check the data set. Thank you.
Let's thank the speaker one more time. Our next presentation is about a thought-provoking paper on the use of living organisms in digital devices. A paper from the University of Chicago. Jasmine Liu will be presenting. Pedro Lopez is the co-author. And the title is Integrating Living Organisms in Devices to Implement Care-Based Interaction. Take it away.
There you go. All right. Hi, everyone. My name is Jasmine Liu, and I'm really excited today to be presenting our work, Integrating Living Organisms and Devices to Implement Care-Based Interactions. To repeat what Eric said, this work was done in collaboration with Pedro Lopez at the University of Chicago. So in this work, we explore how embedding a living organism as a functional component of a device changes the user-device relationship. Okay, we explore this by creating the smartwatch you see here, that clearly it's not a normal smartwatch. Our design incorporates the act of caring for it in its interaction. The organism here acts as a living wire, and you can see it growing across here. Once grown, the organism forms an electrical wire that enables a heart rate sensor. And when connected, it completes the circuit, powering the sensor and enabling the user to see their heart rate. However, this living wire only works when the organism is healthy. In our concept, the user needs to actively care for the living wire in order for the device to work. Here you can see the user providing water as a form of care. So why would we build a device like this that has so much friction and requires the user to actively care for it in order for it to work? Well, in HCI, we design all these innovative interactive devices that are increasingly necessary and integrated into our lives. But despite the large role that they play in your life, have you ever wondered whether you are actually a good caretaker of your devices? I would argue that for the most part, we are not great caretakers of our devices. Once their utility runs out or a newer model gets released, most of our devices become electronic waste in landfills without much of a second thought. In fact, e-waste is the largest growing waste stream in the world. Our work is motivated by exploring how we can reimagine this user-device relationship by engineering our devices differently. Similarly, across various HCI projects, researchers have also imagined alternative relationships by creating devices that encourage non-normative engagements and moments of reflection. Researchers have also specifically explored how to embed care into our interactions with these devices through a variety of methods. Oftentimes, designs involve forms of virtual care, where users care for digital entities like pets or plants. A really great example of this is the Tamagotchi, a toy that asks the user to care for a virtual pet. Interactions based on virtual care work by simulating liveliness to keep the users engaged. However, there is a limit to the attachment formed between user and this virtual companion. The Tamagotchi device is ultimately made up of inert materials like metals and plastics, and after the novelty of the device wears off, it can be hard to feel a connection to such a device. And for a lot of young kids, even if they loved and cared for this toy at one point, they ultimately lost connection and threw them out. So this makes living media interfaces a really interesting area to explore. In these past projects, researchers have looked at what happens when we don't only use inert materials, but instead work with responsive and living organisms. So we're inspired by these past approaches to specifically explore the use of living material to design for caring interactions. So we present our concept of implementing physical care in interactive devices by integrating a living organism. To explain our concept, we use the example of our slime mold integrated smartwatch. But our concept can be realized across various device, organism, and user configurations. To better illustrate this, we present 3 key principles needed for our concept to work. Principle 1, interactive device features a living organism. Our concept relies on the really unique qualities evoked from interaction with a living organism. For one, plastics and metals are not responsive like living organisms, making it difficult to feel kinship with devices made only of such materials. Whether plants, fungi, bacteria, animals, slime mold, or even humans, we all need the right nutrition and environmental conditions to thrive, and this is something that connects us all. And working with living organisms also has quite literally life or death stakes because of these needs. And these are all really unique material qualities that interaction designers can incorporate in partnering with them and highlighting them in their device. Principle 2, the user is responsible for delivering care. So our concept puts the user in charge of the act of care. We do this to avoid the sort of virtual care relationship where delivering care is a frictionless, automated experience, like via a push of a button. In requiring the user to perform care, the user also becomes an active and essential part in this relationship between user, device, and living organism. Last, principle 3, the organism participates in the functionality of the device. To further encourage care, the organism must contribute to some aspect of the interactive device's functionality, and this contribution should be as explicit as possible. If the user immediately recognizes the impact of the organism's health, they can understand the impact of the care that they deliver, offering more potential to deepen this user-device relationship. So these three principles enable the formation of a caring interactions network where all three entities can benefit from the provided care. So now I'll dive deeper into how we implemented this concept. So the living organism we partnered with is Physarum polycephalum, also known as slime mold. So slime mold has a lot of really unique features that make it especially great for designing caring interactions with. It's an organism found in many wet foresty areas, but it's also commonly found in many middle school or high school lab project kits. It's also biosafety level 1, so presents little to no danger when handling it. And as you can see in these pictures, slime mold can grow really expansively and in many different environments. For our purposes, we put slime mold in a small acrylic enclosure designed to encourage the formation of a living wire. Here's a time lapse of it growing across it towards the soaked oats in the second well. As you can see, eventually without enough moisture, the slime mold dries out, entering a dormant state. Slime mold can exist in the dormant state for years, waiting to be resuscitated again when environmental conditions become a little bit more favorable. So let me show you how we use this in our interaction design. Back in our video, I showed you how when the slime mold is fully grown across, healthy, and connected to the smartwatch, it acts as a living wire, conducting electricity to power the heart rate sensor. However, if the user doesn't care for the device and neglects it, over time, the organism will dry without any water to sustain it. And without the necessary conditions to thrive, the slime mold will enter a dormant, dried state. And when it does so, the organism is no longer conductive or connected, disabling the sensor. However, the user can then revive the organism by providing care and over time allowing the slime mold to grow the wire again. So we leverage this extremely unique feature of the slime mold's life cycle to design interactions that depend on the user's care and subsequently the slime mold's health. This works because in our watch, the organism directly participates in the device functionality. This is the schematic of our whole system, and in yellow you can see how the Physarum acts as a living wire, connecting the circuit. We also conducted several tests as a technical evaluation of the slime mold living wire. We explored growing our slime mold with different types of nutrition and on different substrates, testing the influence of direct light on its growth, taking time lapses of the slime mold's growth to determine average speed of growth, and last, measuring the average resistance of the Physarum wire over time. Now, there are many, many limitations of using a living wire, and in many ways, this living wire can't compete with the reliability of a standard copper trace. These tests were done to give better insight into practically how a slime mold wire could be used, but we were more specifically interested in the unique properties of working with it as a living material. So to go back, our original purpose of doing this whole project was to see if our approach could change the user-device relationship. So we wanted to actually give out this new living wearable device and see what folks thought. So we had participants take the device home and wear this device for 9 to 14 days in their daily life. Our study consisted of 2 phases. First, in the caring phase, we instructed participants to care for the Physarum until it grew a wire and they could experience a healthy Physarum and heart rate enabled device. Then we instructed participants to not care for the Physarum until it was dried and the heart rate sensor was no longer enabled. So in the study, we had really, really interesting responses from our participants throughout the study. I selected some quotes to read to you to give you an idea of what it was like, but I highly encourage you to read the paper for some more juicy responses. So during the caring phase, participant 5 actually got sick during her study, but continued to actively take care of her slime during her sickness. In her interview, she explains how the care that she gave to the slime mold was the same as the care that her partner and her were giving to herself. specifically feeding herself oats and drinking a lot of water. During the neglect phase, where participants had to not provide care and wait for the phi serum to dry out, participant 4 explained how during the growing phase, she checked up on the watch more, but after not having to care for it, she treated the watch more like an object. When comparing her experiences with a regular smartwatch, participant 1 explained how the phi serum watch didn't feel like a one-way relationship as she was taking care of it, and the watch was giving her heart rate as payback. This felt more like a bi-directional relationship. And last, in comparing the care that she gave to her other electronic devices compared to her phi serum watch, participant 2 explained how she felt more immediately connected to her phi serum watch because of the living component, feeling connected even on the first day, whereas with other devices, she felt like it takes years. Overall, we found 3 main themes across our participants' experiences. We found that they developed a sense of responsibility for the watch, an affinity to the organism, and a reciprocal relationship, and also experienced affective responses depending on the device's state. So to conclude, as the number of consumer devices grows exponentially, the toll on our environment becomes more pronounced. We primarily engage only as users of our devices, a relationship that only works one way. We see our approach as a method to encourage users to reckon with this aspect of their device use and to explore future possibilities where our designs encourage more than just a user-device relationship built on extractive use, but interactions where users can take on a caretaking role. So the care that we extend to our devices is clearly different from the care that we extend to our other non-human counterparts, like our plants or pets. Could the future of interactive devices also provide enriching experiences that center care for the other? We hope that our work can allow others to imagine these new care-based futures, foster debate, and also inspire novel perspectives on this idea. To end, I'd like to very quickly give a special shout out to the Slime Mold Collective for supplying us slime mold and invaluable knowledge about working with slime mold. We'd actually like to pass the torch by sharing project details at this link. And if you come to our demo that's happening in a bit, you might be able to get your hands on a little slime mold growing kit. So please come. And that's all. Thank you so much for listening to this presentation. Feel free to ask questions.
Thanks, Jasmine. Do we have any questions?
Hi, Jasmine. Thanks for the talk. I'm Vivian from Carnegie Mellon University. I have like a purely speculative question, but I'm wondering how you feel. So this relationship seems pretty simple to me, like you water and you feed it a little bit and it's good. At what point do you think you would find it too laborious for it to be a two-way street, and would you want to kind of stop caring? This is, just opinion speculation.
Yeah, I mean, again, like this whole project is about creating a friction-full experience where you have to enact care for the device. I can imagine like our relationship with a lot of other devices. At some point, there are times where we no longer feel like they're useful and want them in our lives. We actually, in our study, we asked participants a question about what would you do if you decided that you no longer wanted this device in your life. And a lot of participants actually felt conflicted about this. Some participants said that like they felt like they had to rehome it like they would a pet, for example, because of the living element. And some people were like, I don't feel like I could just trash it like a normal device or like keep it in the closet because of this living component. So I think there's some tension there where even if you're tired of taking care of it, you feel like you have responsibility over the slime mold and its health. Hope that answers your question.
This is Lini also from CMU. So you make me wonder whether, like cleaning my lenses or charging my phone also is kind of a care. But the question is also kind of speculative. I'm sure you looked into how to leverage the living material itself to do sensing. So for example, with some genetic modifications, You could have it to sense sweat or physiological. So I wonder if that feels an even smoother sort of closed loop curve, because then you can really take care of the organism that does the actual work versus having electronics in the middle.
Yes, absolutely. I would love to see that future. I do also want to mention something that you brought up, which is like care for our devices can take many forms. And we also like brought that up as a question to participants. So read our paper for more. But yes, I would love to see a future where the organisms we work with can be much more intimate to us, and that we can have more of a symbiotic relationship to them. I'm very inspired by the idea of a holobiome, which the idea in biology is the fact that within us, our guts and stuff, we are kind of climates for a lot of other organisms, bacteria and stuff to thrive. So I feel like there are a lot of pathways that we could take with this relationship, and I'm super excited about the future of what we could do.
Thank you so much. That's all the time we have. So if you'll bear with us for a second, our next presenter will be remote due to COVID protocols. But we are going to zoom her in, and I believe she will be able to see us through this camera here. While we're waiting, I want to remind everyone that if you look in the back of the room, there are QR codes on the door. You can use your phone to scan those codes to get to the vote for the best talk award. We have a lot of great candidates in this session, so don't miss out. All right, this paper is called Waddle Walls, Room Scale Interactive Partitioning System Using a Swarm of Robotic Partitions. Our presenter joining us via Zoom is Yuki Onishi. Other co-authors are Kazuki Takashima, Shoi Higashihima, Kazuyuki Fujita, and Yoshifumi Kimura.
Thank you very much for introducing me. Can you hear me?
Yes, we can. Can we all wave?
So before my presentation, unfortunately, I have a fever and not feeling well today, so I'd like to present my presentation from my hotel room. I'm very sorry to inconvenience, and thank you very much for session chair and program chair, and also my advisors and colleagues for arranging this environment. So let's move on to my presentation. So again, my name is Yuki Onishi. I'm a PhD student of Tohoku University Research Institute of Electrical Communication. Today, I will present Waddle's room-scale interactive partitioning system using a swarm of robotic partitions. I worked this project with Kazuki Takashima, Shoi Higashiyama, Kazuyuki Fujita, and Yoshifumi Kitamura in Tohoku University, Japan. In this work, we introduced Waddle, which is interactive partitioning system with vertically shape-changing robotic partition. If user wants to rearrange the workspace layout, user just need to point the controller at desired locations, and all of a sudden, partitions can move there automatically. Waddle was enabled to dynamically reconfigure workspaces by just designing the layout. Let me explain motivation of this work. Workspace design is crucial for enhancing productivity, promoting social interactions, and also protect personal privacies. In these days, work activities are becoming more diverse, so workspace structures is also becoming more complicated. Therefore, workspace requires layout flexibility to adapt occupants' workflows or requirements. For achieving the adaptive workspace, we assume that physically transformable offices enable to achieve flexible layout changes in response to users' activity. Towards such a transformable office, self-actuated furniture has been actively explored, including moving vertical displays and also self-actuated tabletops. They can dynamically reconfigure themselves, depends on users' formations or content. However, the existing robotic interfaces only facilitate interaction around the device within the single workspace, so not supporting room-scale workspace reconfiguration. So in this work, we explore room-scale workspace partitioning. We focus on partitions that can manage the entire environment spacing. But the regular floor-anchored or wheeled partitions have low flexibility. For example, once a user set up multi-partition in offices, users need to stop the task temporarily, and this manual arrangement also requires high physical workload. Therefore, these limitations bother users optimizing their workspace. To solve this problem, we focus on swarm robotic approach. For example, tabletop-sized swarm robots uses to represent haptic feedback or display multi-dimensional information. And these days, room-scale swarm robots have been also developed recently to provide haptic feedback in VR. So we apply this swarm of robotic approach for controlling multiple partitions for room-scale interactive space reconfiguration. Based on this background, we propose Butterworld, which is room-scale interactive partitioning system using a swarm of robotic partitions enabled to dynamically reconfigure workspace. Before implementation, we explore design consideration of partition system. We designed these 6 design parameters to design dynamically and interactively manage a couple of workspace partitioning. Here is a prototype of our self-actuating robotic partitions. This device consists of 3 main components: actuator using Roomba, and height adjustable lift, and screen. At the top of the screen, we attach the HTC Vive tracker for detecting the partition position. For the actuator's movement, which it controls through serial communication from PC with Bluetooth. And also, this actuator can continuously work about 5 hours with battery. And for the lift, height up and down is switched by the motor control through TCP connection via Wi-Fi. The screen height can be changed from 1.3 meters to 1.8 meters for adapting sitting and standing users. We also design user interfaces to manipulate these Butterworlds. Our interface includes 2 components: controller and visual monitor. For controller, we applied HTC Vive system again and attached the functions for each button. For example, this circles target specify button and also dispatch the partition by trigger button. For the visual monitor, it shows the position of controller and also current position of partitions, and user specify the target position. And light and dark blue circle indicates safety area, which is prohibiting to overlap other safety area to avoid collisions. This shows the software overview of Butterworlds. There are 2 workflows. First one is target specification, and the other one is target motion control. Here is the system workflow. First, user points the controller to specify target location one by one. Once a user registers the target position, target allocator matches the position by solving optimizing algorithm. Then, after partition dispatch, the collision avoidance algorithm calculates path planning to avoid collision based on the detected current position data. So all partitions enable to reach the goal of safety. This collision avoidance algorithm can design the path planning without bumping into each other. Also, from our system evaluation, the average position error was around 2 centimeters, and rotation error was 2 degrees. We also implement two additional manipulation functions. First one is position adjustment for vertical height and lateral positions. And the other one is preset function, partitioning function. If the user layout registered beforehand, partition can be arranged without position specification. By liberating the bottle, we also demonstrate various application scenarios. In this scenario, water was configured temporal personal spot for the private task like calling or taking a nap. User can also put them back after finishing the task. In the next scenario, if the colleagues began the informal meeting around the desk, user can build a personal booth immediately, and he can shut out surrounding noise. On the other hand, height adjustable allows outside users to smoothly transform face-to-face formations with inside users. After discussion, inside user can be higher the partition. In this scenario, multi-user can collocate within the single environment. Water was enabled to separate the rooms dynamically. This usage is effective, for example, keeping situational awareness of head-mounted display user. In the next scenario, if liberty preset function, we can set temporal background to hide messy surrounding environment at online meeting scenario. If we resisted frequently used layout, we can call it by just pushing the button. At last, besides office environment, we can show the swarm of robotic partition manipulation for creating exhibition layout. This example shows the scenario of building poster booths at conference. To evaluate the Waterworld's basic partitioning experiences and architectural potential, we conducted two studies. For the first study, we evaluated overall partitioning workflow and system preferences through NASA TLX and original questions to compare wheel manual partitions. From the results, Waterworld decreases physical and cognitive workflow during the partitioning, and also overall participants significantly preferred our Waterworld system. For the further exploration, we asked 3 experts to discuss further future potential of Waterworlds. From the inside, 3 experts suggest group work facilitation through workspace openness control is more desired. And also, we need to consider the system deployment for real environment, like we need to consider actuating noise effects, and also they're required a large space for driving robotic partitions. About the discussion and future work, there are 4 we provide 4 discussions. At first, we can combine with another actuated furniture interface like tabletop or vertical displays and chairs. And also, in current prototype, we can only change the height adjustable, but as a next step, we can introduce horizontal shape changes and also multidimensional surface deformation. And also, we can collaborate with projection mapping to develop dynamic movable display system. And as a next step, we can consider deployment in the real environment without detecting environmental objects or passengers and considering idle widths and developing more smarter algorithm. And also, we can employ camera-based self-tracking system like depth sensor and ladders. This is the end of my presentation. Thank you very much.
Thank you, Yuki. Any questions? I'll ask one to get us started. If you looked at different passive walls, I'm wondering if you considered how you might actuate the walls or add interactivity to the walls. Have you considered any of that functionality?
Sorry, can you repeat the question? Noise voice is a little bit unclear.
Have you considered adding interactivity to your walls?
Yes, yes. I can hear you now.
Can you hear the question? So my question is, have you considered adding interactivity to the walls in addition to just a physical barrier?
Interactivity means so automated partitioning.
Perhaps using the walls as a screen, as a display, or maybe a touch surface.
I see. In this project, just stop at the partitions, but at the next step, of course, I consider as a display, using as a display to combine with projector and or changing into the LCD display.
Thank you. Any other questions? You can either come up here or I'll repeat the question up here.
Yes. Hey, can you hear me? Or,
yes.
Hey, I'm Ken from the University of Tokyo. Thank you for the presentation. Yeah, I really like the part that the wall was moving up and down when the collaborators came to the person working inside. And well, I thought that part was like very inspiring. That, for example, when I'm really concentrating on my work, then my colleagues like come to my back and tap my back. I get really surprised, like because I was focusing on work. But in that system, like, since the walls like gradually pull down, that in that case, like I can like without being surprised, I can like gradually move the focus from my work to the colleagues in the front. So I'm like looking forward to like doing some user study also like in those aspects of like the moves, what happens to the person when the walls move dynamically. So that was not a question, it was just a comment.
Thank you.
Thank you.
Thank you very much for the nice comment. And of course, my user study is just investigate the partitioning workload. So at the next step, I want to introduce this system into the real office, and also this, I want to office workers try this system and discuss more and more. Thank you.
All right, thank you so much, Yuki, and we hope you feel better. Let's thank Yuki one more time. All right, that concludes our session. Just a few announcements. Again, remember to vote for the Best Talk Award using the QR code on the door. At 7 p.m. in about 45 minutes, we will have the demos. Demos are downstairs, and there's also the Student Innovation Contest in one of the rooms around the corner. And finally, someone lost